In this video, we'll explore how the universe might come to an end, examining different scientific models that predict the ultimate fate of everything we know. Don't forget to subscribe and like this video. And now, I wish you a good night and enjoy listening. Heat death, big freeze. In the grand theater of existence, where galaxies dance their slow waltz across the cosmic stage, there lies a profound question that has captivated minds for generations. What awaits our universe in the distant future? What final act will close the curtain on this magnificent cosmic drama that has been unfolding for nearly 14 billion years? The answer, according to our current understanding of physics and cosmology, points toward a scenario both beautiful and melancholic in its inevitability. It's called the heat death of the universe, or, as some prefer to call it, the Big Freeze. This isn't a catastrophic event in the traditional sense. No explosive finale or dramatic collapse. Instead, it's a gradual, almost gentle transition toward a state of perfect equilibrium, where the universe reaches its maximum entropy and settles into an eternal, peaceful slumber. To understand this cosmic ending, we must first appreciate the fundamental forces that govern our universe. Energy, in all its forms, flows like water seeking its lowest level. Heat moves from warm regions to cool ones. Concentrated matter spreads out into emptiness, and order gradually gives way to disorder. This isn't chaos in the dramatic sense, but rather a natural progression toward balance, like ripples on a pond eventually settling into stillness. The concept of entropy lies at the heart of this story. Entropy is often described as disorder, but it's more accurate to think of it as a measure of how energy spreads out and becomes unavailable for doing work. When you burn a piece of wood, the concentrated chemical energy transforms into heat and light that disperses into the environment. That energy still exists, but it's now scattered and diluted, unable to be gathered back together to burn the wood again. Our universe operates under this same principle on the grandest possible scale. Stars burn their nuclear fuel, converting hydrogen into heavier elements, and releasing tremendous amounts of energy. Galaxies collide and merge, their gravitational potential energy transforming into heat and motion. Black holes evaporate through Hawking radiation, slowly returning their mass energy to the cosmos. Each of these processes increases the total entropy of the universe, pushing it ever closer to its final equilibrium state. The journey toward heat death began the moment our universe came into existence. In those first fractions of a second after the Big Bang, the cosmos was in an extremely low entropy state. Matter and energy were concentrated and organized in ways that seem almost miraculous when viewed from our current perspective. The slight irregularities in density that would eventually become galaxies, stars, and planets were like tiny seeds of future complexity planted in an otherwise smooth and uniform expanse. As the universe expanded and cooled, these seeds began to grow. Gravity pulled matter together, creating the first stars and igniting the nuclear furnaces that would illuminate the cosmos for billions of years. These early stellar generations lived fast and died young, exploding as supernovae and scattering the heavy elements necessary for rocky planets and life itself throughout space. The universe we inhabit today represents a middle chapter in this cosmic story. We live in what astronomers call the stelliferous era, an age dominated by star formation and nuclear burning. Our sun, a middle-aged star by cosmic standards, will continue to shine steadily for another 5 billion years or so. Across the galaxy, new stars are born in stellar nurseries like the Orion Nebula, while others reach the end of their lives and return their enriched material to the interstellar medium. But this period of abundant star formation cannot last forever. The universe is gradually using up its supply of hydrogen, the primary fuel for stellar nuclear reactions. Like a vast cosmic bonfire slowly consuming its wood, the rate of star formation has already peaked and begun its inexorable decline. We're living in the golden age of stars, and that age is already beginning to wane. The process is so gradual that it's difficult to appreciate from our human perspective. Over the next trillion years, star formation will continue to slow as the universe's hydrogen supply becomes increasingly depleted. The most massive stars, which burn their fuel quickly and shine brilliantly, will be the first to disappear. These stellar giants live for only millions of years before exhausting their nuclear fuel and ending their lives in spectacular supernova explosions. As the universe ages, only the smallest, most efficient stars will remain. Red dwarfs, stars with less than half the mass of our Sun, are remarkably frugal with their nuclear fuel. They burn hydrogen so slowly and efficiently that they can continue shining for trillions of years. In the far future, these dim red stars will be the universe's primary source of light and warmth. Their feeble glow, the last defense against the encroaching cold. But even these miserly stars cannot burn forever. The laws of thermodynamics are patient but implacable. Eventually, even the longest-lived red dwarfs will exhaust their hydrogen supply and fade into darkness. When this happens, roughly 100 trillion years from now, the universe will enter what cosmologists call the Degenerate era. During this vast epoch, the cosmos will be populated primarily by stellar remnants. White dwarf stars, the cooling embers of medium-sized stars like our Sun, will slowly radiate away their remaining heat over hundreds of trillions of years. Neutron stars, the ultra-dense cores left behind by massive stellar explosions, will continue their rapid rotation, gradually slowing as they lose energy through magnetic braking and gravitational wave radiation. Black holes of various sizes will dot the cosmic landscape like gravitational lighthouses, their presence detectable only through their effect on nearby matter and space-time itself. The largest of these, the supermassive black holes that currently reside at the centers of galaxies, will have grown even more massive by consuming surrounding material and merging with their counterparts in other galaxies. Planets, if they still exist, will be frozen worlds orbiting the slowly cooling remnants of their parent stars. Any remaining atmospheres will have long since condensed and frozen to their surfaces. The Earth, if it somehow survives the Sun's eventual expansion into a red giant star, will be a lifeless ball of ice drifting through space around a slowly cooling white dwarf. But the Degenerate era, vast as it is, represents only an intermediate stage in the universe's journey toward heat death. The stellar remnants that populate this era are still sources of energy gradients and organizational structure. White dwarfs still glow with residual heat. Neutron stars still spin with rotational energy. And planetary systems still maintain their orbital configurations through gravitational binding. Over truly astronomical timescales, even these last bastions of organization will succumb to the universe's drive toward equilibrium. Protons, the building blocks of ordinary matter, may themselves be unstable over periods of 10 to the power of 34 years or more. If grand unified theories of physics are correct, these fundamental particles will eventually decay, breaking down the very atoms that comprise planets, stellar remnants, and everything else made of ordinary matter. The decay of protons would mark the beginning of the black hole era, when these gravitational anomalies become the dominant structures in the universe. But even black holes are not eternal. Stephen Hawking's groundbreaking work showed that black holes slowly evaporate through quantum effects at their event horizons. Virtual particle pairs, constantly appearing and disappearing in the quantum vacuum, occasionally become real when one particle falls into the black hole while the other escapes. This Hawking radiation causes black holes to slowly lose mass over time. The process is incredibly slow for large black holes. A black hole with the mass of our Sun would take 10 to the power of 67 years to evaporate completely. The supermassive black holes at galactic centers would require even longer, perhaps 10 to the power of 100 years or more. But time is the one resource the universe has in unlimited supply. As black holes evaporate, they release their mass energy back into the universe in the form of elementary particles and radiation. Ironically, the final moments of a black hole's existence are the most dramatic, as the evaporation process accelerates exponentially as the black hole's mass decreases. What began as a barely perceptible trickle of Hawking radiation becomes a torrent, and finally a brilliant flash as the last remnants of the black hole disappear into the quantum vacuum. When the last black hole evaporates, the universe will enter its final era. The cosmos will consist primarily of a thin soup of elementary particles, photons, neutrinos, electrons, positrons, and perhaps other stable particles predicted by various theories of physics. These particles will be spread so thinly that the average distance between them could be larger than our current observable universe. At this point, the universe will have reached a state very close to maximum entropy. The temperature everywhere will be just barely above absolute zero, maintained only by the slow expansion of space itself. There will be no energy gradients to drive the complex processes that once created stars, planets, and life. The cosmos will have achieved perfect equilibrium, a state of complete thermodynamic balance. Yet, even in this seemingly lifeless future, the universe will not be entirely static. Quantum mechanics ensures that the vacuum itself is never completely empty or motionless. Virtual particles will continue to appear and disappear in brief quantum fluctuations. On incredibly rare occasions, these fluctuations might be large enough to create small amounts of matter and energy, like distant echoes of the creative forces that once filled the cosmos with light and complexity. Some physicists speculate about even more exotic possibilities in this far future. In a universe where entropy has reached its maximum, incredibly rare quantum events might occasionally create pockets of lower entropy, perhaps even giving rise to new regions of space-time that could evolve their own physics and structures. These would be like tiny universes bubbling up from the quantum foam, each potentially developing its own unique properties, and perhaps even its own forms of complexity and organization. The timescales involved in this ultimate future are so vast that they challenge our ability to comprehend them. The current age of the universe, 13.8 billion years, is less than an instant compared to the epochs we're discussing. If the entire history of the universe from the Big Bang to the present were compressed into a single second, the era of stellar burning would last about 10,000 years, and the final approach to heat death would stretch on for trillions upon trillions of centuries. This vision of the universe's ultimate fate might seem bleak or depressing, but there's also something deeply beautiful about it. The heat death represents the cosmos reaching a state of perfect peace and balance. All the turbulence and violence of cosmic evolution, all the stellar explosions and galactic collisions, all the frantic nuclear burning and gravitational collapse will finally give way to serene tranquility. In this final state, the universe will have fulfilled the deepest imperatives of physics. Energy will be distributed as evenly as possible. Entropy will have reached its maximum value, and the cosmos will have achieved the ultimate expression of thermodynamic equilibrium. It's a kind of cosmic enlightenment, where all the restless energy and matter that once drove the grand drama of cosmic evolution will have found their perfect rest. The journey toward this ultimate equilibrium is itself a story of remarkable beauty and complexity. Along the way, the universe will have created countless wonders, galaxies spiraling through space, stars igniting in brilliant nuclear furnaces, planets forming from cosmic dust, and perhaps life arising to contemplate its own existence and ponder the very questions we're exploring now. From our current vantage point, midway through the universe's stellar age, we're witnesses to an extraordinary phase of cosmic evolution. We live in an era of abundant energy and active star formation, when the universe is still young and vigorous enough to create new complexity and organization. The light from distant galaxies carries the story of cosmic evolution across billions of years, allowing us to see the universe as it was in its youth and to understand the processes that will shape its future. The heat death scenario is based on our current understanding of physics and cosmology, particularly the laws of thermodynamics and our observations of cosmic expansion. The universe appears to be expanding at an accelerating rate, driven by dark energy, which makes it increasingly unlikely that gravity will ever reverse the expansion and cause a cosmic collapse. Instead, space will continue to grow larger and colder, diluting matter and energy until equilibrium is achieved. This understanding represents one of humanity's greatest intellectual achievements. Through careful observation, mathematical analysis, and theoretical insight, we've been able to peer forward through deep time and glimpse the ultimate fate of everything we know. It's a testament to the power of scientific inquiry and the remarkable capacity of conscious beings to understand their place in the cosmic story. The heat death of the universe reminds us that we're living in a special time, when stars shine brightly and complex structures can form and evolve. Our existence, and that of all life in the universe, depends on the temporary imbalance between energy and entropy that characterizes this cosmic epoch. We are, in a very real sense, children of the stars, made possible by the universe's journey from its highly organized initial state toward its final equilibrium. In contemplating this vast future, we might find both humility and wonder. The universe is far larger and older than human civilization, and it will continue long after our sun has faded and our galaxy has dispersed. Yet, we're also part of this grand story, temporary expressions of the universe's capacity for self-organization and self-awareness. Through us, the cosmos has developed the ability to understand itself and to contemplate its own destiny. The heat death may be the universe's final chapter, but it's not a tragedy. It's simply the natural conclusion of a story that began with the Big Bang and will end with the gentle settling of all energy into perfect equilibrium. Along the way, this cosmic drama will have created beauty, complexity, and consciousness on a scale that's difficult to fully appreciate. And in that ultimate quiet, when the last light has faded and the final particle has found its rest, the universe will have achieved something profound: perfect peace, perfect balance, and the complete fulfillment of the physical laws that have guided its evolution from the very beginning. Big Crunch. There exists another vision of cosmic destiny, one that stands in stark contrast to the gentle fade of heat death. Instead of an eternal expansion into cold emptiness, this scenario imagines a universe that will one day reverse its outward journey and begin the long fall back toward unity. This is the Big Crunch, a cosmic story of expansion followed by contraction, of a universe that breathes in after breathing out, returning to the dense, hot state from which it originally emerged. The Big Crunch represents one of the most elegant and symmetrical possibilities for our universe's future. If the gentle dissolution of heat death is like watching a flower slowly wilt and scatter its petals to the wind, then the Big Crunch is like watching a film of cosmic evolution played in reverse. Galaxies that have spent billions of years moving apart would begin to approach each other once again. The vast emptiness between cosmic structures would shrink, and the universe would embark on a journey back toward the conditions that existed in its earliest moments. To understand how such a dramatic reversal could occur, we must first appreciate the delicate balance of forces that govern a cosmic evolution. Since the Big Bang, two fundamental influences have shaped the universe's destiny. Expansion, driven initially by the explosive energy of creation itself, and later by the mysterious dark energy, pushes everything apart. Gravity, working patiently across cosmic distances, tries to pull everything back together. The ultimate fate of the universe depends on which of these forces proves stronger over the vast scales of space and time. Current observations suggest that dark energy dominates, accelerating the universe's expansion and making heat death the most likely scenario. But the Big Crunch remains a fascinating possibility, one that could unfold if our understanding of dark energy proves incomplete, or if the fundamental properties of space-time change over cosmic time. In this alternative future, gravity would eventually overcome the forces of expansion, perhaps triggered by changes we cannot yet foresee, or by the discovery that dark energy is not as permanent as we currently believe. The transition from expansion to contraction would not happen suddenly. Like a ball thrown into the air that gradually slows, stops, and begins to fall, the universe would first decelerate its expansion until it reached a moment of maximum size. This cosmic turning point would mark the end of the expansion phase that has characterized our universe for nearly 14 billion years. From our perspective within the universe, this moment might be barely noticeable at first, detectable only through the most precise measurements of cosmic distances and velocities. Imagine standing in a vast cosmic observatory in this distant future, perhaps tens of billions of years from now, watching as the Hubble constant gradually decreases towards zero. The galaxies that have been receding from us throughout cosmic history would slow their retreat, like dancers in a cosmic ballet preparing to reverse their choreography. The cosmic microwave background radiation, the afterglow of the Big Bang that currently fills all of space, would begin to shift toward higher frequencies as the universe's contraction compresses these ancient photons. As the universe begins its inward journey, the changes would initially be subtle. Galaxies would start moving toward each other rather than away, but their speeds would be small at first. The vast distances between galactic clusters would begin to shrink, Though the process would unfold over billions of years, stars would continue to shine, planets would maintain their orbits, and the basic structure of cosmic life would remain largely unchanged during these early phases of contraction. But as the universe grows smaller and denser, the pace of change would accelerate. The same gravitational forces that once struggled against expansion would now work in harmony with the universe's inward motion, creating a feedback loop that drives increasingly rapid contraction. Galaxy clusters would merge more frequently as the distances between them diminish. The night sky would gradually brighten as more and more distant galaxies come within range of observation, their light no longer redshifted by expansion, but instead blue-shifted by the universe's contraction. The cosmic web, that magnificent large-scale structure of galaxies and dark matter filaments that currently spans billions of light years, would begin to collapse in on itself. The vast voids between galaxy clusters would shrink, concentrating matter and energy into increasingly dense regions. This process would happen unevenly, with some regions contracting faster than others, creating a complex pattern of cosmic evolution as different parts of the universe approach each other at different rates. As the contraction continues, the increased density would have profound effects on the formation and evolution of cosmic structures. Star formation rates would likely increase as gas clouds are compressed by the universe's overall contraction. The interstellar medium would become denser and more turbulent, leading to more frequent stellar births and potentially more massive stars than we see today. Galaxies would experience more frequent encounters and mergers as the space between them continues to shrink. The cosmic microwave background, that faint radiation left over from the universe's hot, dense beginning, would grow progressively hotter as the contracting universe compresses these ancient photons. Currently at a temperature of about 2.7 Kelvin above absolute zero, this radiation would begin to warm as the universe shrinks. Eventually, it would become hot enough to affect the thermal environment of planets and stars, adding an additional source of energy to cosmic structures. Black holes, those gravitational monsters that currently exist as isolated objects scattered throughout galaxies, would find themselves in an increasingly target-rich environment. As matter becomes denser and gravitational fields stronger, more material would fall into existing black holes, causing them to grow rapidly. New black holes would form more frequently as the compressed matter reaches the critical densities necessary for gravitational collapse. The merger of galaxy clusters would become increasingly common and violent as the universe continues to contract. These cosmic collisions, which currently occur rarely and over vast timescales, would happen more frequently and with greater energy. The dark matter halos that surround galaxies would interact and merge, reshaping the gravitational landscape on the largest scales. The beautiful spiral structure of galaxies like our own Milky Way would likely be disrupted by these increasingly frequent gravitational encounters. As the universe approaches perhaps 1% of its current size, the effects of contraction would become impossible to ignore, even on planetary scales. The cosmic microwave background would be hot enough to warm planetary surfaces, potentially boiling away atmospheres and oceans that had survived billions of years of stellar evolution. The increased density of matter would affect planetary orbits and the stability of solar systems as gravitational interactions become stronger and more chaotic. Stars themselves would be affected by the changing cosmic environment. The higher background temperature would alter their energy balance and evolutionary timescales. Stellar formation would likely increase dramatically as gas clouds are compressed not just by local gravitational forces, but by the overall contraction of space itself. The universe might experience a final burst of stellar activity, a brilliant renaissance of star formation before the conditions become too extreme for stable nuclear burning. The final phases of the Big Crunch would unfold with increasing drama and speed. As the universe contracts to a tiny fraction of its current size, temperatures and densities would soar to levels not seen since the earliest moments after the Big Bang. The cosmic microwave background would become so hot that it would overwhelm the light from stars and galaxies, filling the universe with intense radiation. Matter would be squeezed to such extreme densities that the boundaries between individual particles begin to blur. In these ultimate moments, the very fabric of space-time would be stretched to its limits. The gravitational fields would become so intense that they would affect the fundamental structure of matter itself. Atoms would be crushed beyond recognition, their electrons stripped away, and their nuclei compressed into exotic forms of matter. The distinction between matter and energy would become meaningless as temperatures soar beyond anything that exists in the core of the most massive stars. Black holes, which had grown enormously during the contraction phase, would begin to merge with increasing frequency. The gravitational waves produced by these cosmic collisions would shake the very foundations of space-time, creating ripples that travel at the speed of light through a universe that has become incredibly small and dense. Eventually, all the black holes in the universe might merge into a single, enormous gravitational anomaly containing all the mass and energy that once filled cosmic space. The final moments of the Big Crunch would see temperatures and densities approaching those that existed in the first fraction of a second after the Big Bang. The four fundamental forces of nature, gravity, electromagnetism, and the strong and weak nuclear forces, might once again merge into a single unified force as they did in the universe's earliest moments. The distinction between space and time might break down entirely as the curvature of space-time becomes infinite. Some theoretical physicists speculate that the Big Crunch might not represent the absolute end of everything, but rather a transition to a new phase of cosmic existence. Just as the Big Bang marked the beginning of our current universe, the Big Crunch might trigger a new Big Bang, creating a cyclic universe that expands and contracts in an eternal rhythm. In this scenario, our universe would be just one cycle in an infinite series of cosmic deaths and rebirths, each expansion and contraction phase lasting hundreds of billions of years. This cyclic model suggests that the Big Crunch would compress all matter and energy into a state of infinite density and temperature, similar to the original Big Bang singularity. The laws of physics as we understand them would break down completely in this extreme environment. But from this cosmic crucible, a new universe might emerge, expanding outward with fresh energy and creating new space for matter, stars, galaxies, and perhaps even life to evolve once again. The idea of a cyclic universe has deep philosophical implications. It suggests that time itself might be cyclic rather than linear, with each cosmic cycle potentially lasting much longer than human civilization has existed. The structures we see today, galaxies, stars, planets, and all the complexity of the cosmic web, would be temporary patterns that emerge during the expansion phase of each cycle, only to be erased and recreated in the next cosmic iteration. Different versions of cyclic cosmology propose various mechanisms for how the transition from Big Crunch to Big Bang might occur. Some involve exotic physics beyond our current understanding, while others rely on modifications to Einstein's theory of general relativity. In some models, each cosmic cycle might be slightly different from the last, with variations in the fundamental constants of physics, or the initial conditions that give rise to different evolutionary pathways. The Big Crunch scenario also raises fascinating questions about the nature of information and causality across cosmic cycles. Would any trace of our current universe survive the crushing compression of the Big Crunch to influence the next cosmic expansion? Could the patterns of matter and energy that create galaxies, stars, and potentially life be somehow preserved through the cosmic recycling process? Or would each new universe be a completely fresh start with no memory of what came before? From our current perspective, living in an apparently accelerating universe dominated by dark energy, the Big Crunch might seem like an obsolete idea. But our understanding of cosmic evolution is still incomplete. Dark energy remains one of the greatest mysteries in physics, and its properties over cosmic time are largely unknown. It's possible that dark energy could weaken or even reverse its effects over timescales much longer than the current age of the universe. Some theoretical models suggest that dark energy might not be constant, but could oscillate or decay over cosmic time. If the expansion of space is driven by a scalar field similar to the inflaton field, thought to drive cosmic inflation, this field might eventually roll to a different state that favors contraction rather than expansion. Such changes could occur over timescales of hundreds of billions or even trillions of years, far longer than the current age of the universe. The Big Crunch represents one of the most dramatic possible endings for our cosmic story. Instead of the gentle fade toward equilibrium envisioned in heat death, it offers a spectacular finale where all the matter and energy of the universe comes together in a final, brilliant compression. It's a vision that emphasizes the fundamental unity underlying cosmic diversity, suggesting that everything we see around us, from the smallest particles to the largest galactic clusters, shares a common origin and might one day return to that unified state. This scenario also highlights the deep connection between the universe's beginning and its potential end. The Big Bang and Big Crunch are mirror images of each other: explosive expansion followed by gravitational collapse, creation followed by destruction, or perhaps more accurately, transformation. The matter and energy that emerge from the Big Bang and potentially return to it in a Big Crunch represent the same fundamental substances, cycling through different forms and arrangements as the universe expands and contracts. In contemplating the Big Crunch, we're reminded of the dynamic nature of cosmic evolution. The universe is not a static stage on which events unfold, but an active participant in its own story. The expansion of space, the evolution of matter and energy, and the formation of complex structures are all part of a grand cosmic dance that might one day reverse direction and return to its starting point. Whether or not the Big Crunch represents the actual fate of our universe, it serves as a powerful reminder of the forces that shape cosmic evolution: gravity and expansion, matter and energy, space and time. These fundamental aspects of reality are locked in a cosmic struggle whose outcome will determine the ultimate destiny of everything we know. The Big Crunch stands as testament to gravity's patient power, and to the possibility that what was once unified might one day become unified again, completing the circle of cosmic existence in a final, magnificent convergence. Big Rip. In the pantheon of cosmic endings, there exists a scenario so extraordinary that it challenges our very understanding of space, time, and the forces that bind matter together. This is the Big Rip, a vision of universal dissolution that goes beyond the gentle expansion toward heat death or the dramatic reversal of the Big Crunch. It imagines a future where the fabric of space itself becomes so violently stretched that it tears apart every structure in the universe, from the largest galactic clusters down to the smallest atoms, unraveling the very foundations of physical reality. The Big Rip emerges from our growing understanding of dark energy, that mysterious force responsible for the accelerating expansion of our universe. Unlike gravity, which weakens with distance, dark energy appears to maintain constant density, even as space expands. This means that as the universe grows larger, the total amount of dark energy increases, while the gravitational influence of matter becomes increasingly diluted across the growing cosmic volume. Currently, dark energy makes up approximately 70% of the universe's total energy density, with dark matter contributing about 25%, and ordinary matter comprising just 5%. But these proportions are not fixed. As expansion continues, the density of matter decreases as it spreads through an ever larger volume, while dark energy maintains its strength. This shifting balance means that dark energy's dominance will only grow more pronounced with time. Most models of dark energy assume it behaves like Einstein's cosmological constant, maintaining steady pressure as the universe expands. But the Big Rip scenario emerges when we consider the possibility that dark energy might not remain constant. Instead, it could be what physicists call phantom dark energy, a form of energy that actually grows stronger over time, creating an equation of state parameter less than -1. This seemingly small technical distinction has profound implications for the universe's future. While constant dark energy leads to exponential expansion and eventual heat death, phantom dark energy drives super-exponential expansion that accelerates without limit. The expansion rate doesn't just increase, it increases at an increasing rate, creating a runaway feedback loop that ultimately overwhelms every other force in the universe. The journey toward the Big Rip would begin subtly, much like the current epoch of accelerated expansion. For billions of years, the changes would be barely perceptible even to the most sophisticated instruments. Galaxies would continue to recede from each other at accelerating rates, but the acceleration itself would gradually intensify in ways that might initially seem like minor variations in the measurements. The first signs of the coming catastrophe would appear on the largest scales, in the realm of galaxy clusters and the cosmic web. These vast structures, held together by the collective gravitational influence of countless galaxies and their dark matter halos, represent some of the most weakly bound systems in the universe. As phantom dark energy grows stronger, it would begin to overcome the gravitational forces that maintain these cosmic associations. Galaxy clusters, those magnificent collections of hundreds or thousands of galaxies bound together by gravity, would be among the first casualties. The space between their member galaxies would expand at an accelerating rate, stretching the gravitational bonds until they snap. Individual galaxies would be cast adrift, their ancient gravitational partnerships dissolved by the relentless expansion of space itself. The Virgo cluster, the nearest major galaxy cluster to our own local group, contains over 1,000 galaxies spread across a region about 51 million light-years in diameter. In the Big Rip scenario, this cosmic community would gradually disperse as the expansion of space overcomes the cluster's gravitational cohesion. Galaxies that have been gravitationally bound for billions of years would begin their final journey away from each other, accelerating into the growing emptiness. As phantom dark energy continues to strengthen, smaller gravitational systems would face the same fate. The local group, our cosmic neighborhood containing the Milky Way, Andromeda, and dozens of smaller galaxies, would eventually succumb to the inexorable expansion. The anticipated collision between the Milky Way and Andromeda, currently expected to occur in about 4 billion years, might never happen if the Big Rip timeline overtakes gravitational merger. But the dissolution would not stop at the scale of galaxy groups and clusters. As phantom dark energy grows ever more dominant, it would begin to affect progressively smaller and more tightly bound systems. Individual galaxies, held together by the combined gravitational influence of billions of stars and vast halos of dark matter, would find their spiral arms stretching and distorting as space expands within them faster than their internal gravity can compensate. The beautiful spiral structure of galaxies like our own Milky Way would be among the casualties of this cosmic stretching. The density waves that maintain spiral arms, the gravitational interactions that shepherd star formation in galactic disks, and the delicate balance between rotation and gravitational binding would all be disrupted by the ever-strengthening expansion of space. Stars would be pulled away from their galactic homes, scattered into the growing voids between former galactic boundaries. Even more remarkably, the Big Rip would eventually overcome the gravitational bonds that hold individual star systems together. Our solar system, maintained by the Sun's gravitational influence over a region nearly 2 light-years in diameter, would face dismemberment as space expands faster than gravity can maintain orbital stability. The outer planets would be the first to go. Their distant orbits stretch beyond the point where solar gravity can hold them. Neptune, currently orbiting at an average distance of about 30 astronomical units from the Sun, would gradually spiral outward as expanding space overcomes solar gravity. Uranus, Saturn, and Jupiter would follow in sequence, each planet torn from its ancient orbital dance and cast into interstellar space. Eventually, even the inner planets would be affected, with Mars, Earth, Venus, and finally Mercury losing their gravitational connection to the Sun. The timeline for these events depends on the specific properties of phantom dark energy, but some models suggest the dissolution of galaxy clusters might occur roughly 20 billion years from now, with individual galaxies disrupted, perhaps 10 billion years later. Solar systems could face disruption within the final few million years before the ultimate rip, a cosmic eye blink compared to the billions of years required for the earlier phases. But the Big Rip would not stop even at the dissolution of planetary systems. As phantom dark energy continues to grow stronger, it would begin to affect the very atoms that make up ordinary matter, the electromagnetic forces that bind electrons to nuclei, creating the chemical elements that form planets, stars, and everything we see around us, would face an unprecedented challenge from the expanding fabric of space itself. The atomic scale represents a realm of incredibly strong forces compressed into tiny volumes. The electromagnetic attraction between protons and electrons is enormously powerful compared to gravitational forces, which is why atoms maintain their structure even in the intense gravitational fields near black holes or neutron stars. But phantom dark energy, if it grows strong enough, could eventually overcome even these fundamental interactions. In the final moments before the Big Rip, atoms would be stretched apart as space expands faster than electromagnetic forces can maintain atomic structure. Electrons would be torn away from their nuclei, leaving behind a universe filled with isolated subatomic particles racing away from each other at incredible speeds. The chemical elements forged in stellar cores over billions of years would cease to exist as coherent structures. Even atomic nuclei, bound together by the strongest force in nature, might not survive the ultimate stretching of space. The strong nuclear force that holds protons and neutrons together in atomic cores operates over incredibly small distances, typically less than a femtometer. If space expands rapidly enough, it could overcome even this fundamental interaction, breaking apart the nuclei of every element in the universe. The final moments of the Big Rip would see the complete dissolution of matter as we understand it. Every structure that has ever existed, from the cosmic web of galaxies down to the quarks and leptons that make up individual particles, would be torn apart by the runaway expansion of space. The universe would become a rapidly expanding soup of isolated fundamental particles, each racing away from all others at velocities that approach the speed of light. Some theoretical models suggest that even space-time itself might not survive the Big Rip. If phantom dark energy continues to strengthen without limit, it could eventually overcome the very structure of space-time, leading to what physicists call a finite-time singularity. At this point, the expansion rate would become infinite, the curvature of space-time would diverge, and the laws of physics as we understand them would break down completely. The timescale for the Big Rip depends critically on the properties of dark energy, which remain poorly understood despite decades of observational and theoretical work. If dark energy behaves like Einstein's cosmological constant, the Big Rip will never occur, and the universe will instead experience the gradual heat death described in other scenarios. But if dark energy has phantom properties, the Big Rip could unfold over time scales ranging from tens of billions to hundreds of billions of years. Current observations of cosmic expansion provide some constraints on dark energy's behavior, but they are not yet precise enough to definitively rule out phantom dark energy. The equation of state parameter, which determines whether dark energy leads to exponential expansion or the runaway growth toward a Big Rip, appears to be very close to -1 based on current measurements. Small deviations from this critical value could have enormous implications for the universe's ultimate fate. Interestingly, the Big Rip scenario suggests that the universe's future might be fundamentally different from its past. While cosmic evolution has generally proceeded from simple to complex, from smooth to structured, from hot to cool, the Big Rip represents a phase transition toward ultimate simplicity. Every complex structure that has ever formed would be reduced to its most fundamental components, scattered across an exponentially expanding space. This vision of cosmic destiny raises profound questions about the nature of physical law and the limits of scientific understanding. If phantom dark energy exists and drives the universe toward a Big Rip, it would represent a form of cosmic evolution that has no parallel in the universe's past. The expansion that began with the Big Bang and proceeded through phases of matter domination and dark energy. Domination would culminate in a completely unprecedented era of runaway acceleration. The Big Rip also highlights the interconnected nature of cosmic structure across all scales. We typically think of atoms, solar systems, galaxies, and galaxy clusters as distinct types of objects governed by different physical laws. But the Big Rip scenario demonstrates how a single phenomenon, the accelerating expansion of space, could eventually overwhelm every type of structure in the universe, regardless of the forces that bind them together. From our current perspective, living in a universe where complex structures continue to form and evolve, the Big Rip might seem like science fiction, but it represents a serious possibility based on our understanding of cosmic expansion and the mysterious properties of dark energy. The scenario serves as a reminder that the universe's future remains genuinely uncertain, dependent on physical processes that we are only beginning to understand. The possibility of phantom dark energy and the Big Rip also underscores the importance of precision cosmology in determining the universe's fate. Small differences in the equation of state parameter, perhaps detectable only through the most careful observations of distant supernovae, cosmic microwave background fluctuations, and gravitational lensing, could determine whether the universe faces gentle heat death or catastrophic dissolution. Current and future astronomical surveys, including space-based telescopes and ground-based observatories, are working to measure dark energy's properties with unprecedented precision. These observations will help determine whether phantom dark energy exists, and if so, what timeline might govern the approach toward a big rip. The stakes of these measurements could not be higher, as they bear directly on the ultimate fate of every structure in the universe. The Big Rip represents perhaps the most dramatic possible ending to the cosmic story. A finale that would erase not just complex structures like galaxies and planets, but the very atoms that make up ordinary matter. It's a vision of dissolution so complete that it would undo the results of nearly 14 billion years of cosmic evolution in a final burst of exponential expansion. Yet even in this extreme scenario, there might be a strange kind of elegance. The Big Rip would represent the ultimate triumph of expansion over contraction, of dark energy over gravity, of cosmic acceleration over all the forces that create and maintain structure. It would be a universe reduced to its most fundamental elements, a cosmos that has expanded so completely that every particle exists in perfect isolation, racing away from all others through an infinitely growing expanse of space. Whether or not the Big Rip represents our universe's actual destiny, it serves as a powerful reminder of the dynamic forces that shape cosmic evolution. The balance between expansion and gravity, between dark energy and matter, between structure formation and dissolution, remains delicately poised. Small changes in fundamental parameters could lead to vastly different outcomes. From the gentle fade of heat death, to the dramatic reversal of the Big Crunch, to the ultimate dissolution of the Big Rip. In contemplating this most extreme of cosmic endings, we gain perspective on the remarkable nature of our current epoch. We live in a time when complex structures can form and persist, when gravity can overcome expansion on local scales, when atoms remain stable and chemistry remains possible. The Big Rip reminds us that these conditions might not be permanent features of cosmic existence, but rather temporary phases in an ongoing evolution that could lead to futures more strange and dramatic than we can easily imagine. Vacuum decay, false vacuum collapse. In the deepest foundations of physical reality lies a possibility so subtle yet profound that it redefines our understanding of stability itself. This is the scenario of vacuum decay, also known as false vacuum collapse, where the very ground state of existence might not be as solid as it appears. Unlike other cosmic endings that unfold over billions of years through the gradual evolution of matter and energy, vacuum decay suggests that our universe might exist in a fundamentally unstable state, perched on the edge of a quantum cliff from which it could tumble at any moment into a completely different form of reality. To understand this remarkable possibility, we must venture into the realm of quantum field theory, where empty space is not truly empty, but filled with invisible energy fields that permeate every corner of the universe. These quantum fields form the foundation of all matter and forces, creating the stage upon which the drama of physics unfolds. What we perceive as the vacuum of space is actually a complex tapestry of field energies, each seeking its lowest possible state, much like water flowing downhill to find the deepest valley. The concept of vacuum stability rests on a deceptively simple question. Are the quantum fields that fill our universe truly in their lowest possible energy state? Or might they exist in what physicists call a false vacuum? Imagine standing on what appears to be the floor of a valley, only to discover that you're actually on a ledge partway down a much deeper canyon. The ground beneath your feet seems stable, but it's actually a temporary resting place above an even lower level that you cannot yet see. In quantum field theory, this metaphorical landscape becomes literal through the concept of potential energy surfaces. Every field that exists in nature, from the electromagnetic field that governs light and magnetism to the Higgs field that gives particles their mass, possesses what physicists call a potential energy function. This mathematical description determines how the field behaves at different values, creating hills and valleys in an abstract energy landscape that governs the field's preferred states. The Higgs field provides the most immediate example of this phenomenon in our current understanding of physics. Discovered at the Large Hadron Collider in 2012, the Higgs field fills all of space with a non-zero value that breaks the symmetry between different fundamental forces and gives mass to elementary particles. But the shape of the Higgs potential energy function remains uncertain in its details, particularly at energy scales far beyond what we can currently probe experimentally. Current measurements suggest that the Higgs field might exist in what appears to be a stable minimum of its potential energy function. But more precise calculations, incorporating the effects of quantum corrections and the interactions between the Higgs field and other fundamental fields, hint at a more complex picture. The valley in which our universe currently resides might not be the deepest possible valley, but rather a local minimum, separated by an energy barrier from an even lower state. If this interpretation proves correct, our universe would exist in what physicists term a metastable vacuum state. Like a ball balanced in a shallow depression on a hillside, the Higgs field would be stable against small perturbations, but vulnerable to larger disturbances that could push it over the energy barrier and into the true vacuum state. Such a transition would fundamentally alter the properties of space itself, changing the masses of particles, the strengths of forces, and the very nature of matter. The process of vacuum decay would begin with the spontaneous formation of a bubble of true vacuum somewhere in space. Quantum mechanics allows for the possibility that even seemingly impossible events can occur through quantum tunneling, where systems can transition between states without having the classical energy required to surmount the barrier between them. In the case of vacuum decay, this means that a small region of space could spontaneously transition from false vacuum to true vacuum, creating a bubble of fundamentally different physics surrounded by our familiar reality. This bubble of true vacuum would initially be microscopic, perhaps smaller than an atomic nucleus, but it would possess a crucial property. It would be energetically favorable compared to the surrounding false vacuum. The difference in energy density between the true and false vacuum states would create a pressure that drives the bubble to expand at an ever-increasing rate. The boundary between true and false vacuum would propagate outward at a velocity that approaches the speed of light, consuming false vacuum and converting it to true vacuum with perfect efficiency. The expansion of such a bubble would be relentless and unstoppable. Unlike other cosmic phenomena that are subject to opposing forces or balancing mechanisms, vacuum decay represents a one-way transition toward a lower energy state. Nothing in the false vacuum region ahead of the bubble could slow or stop its advance, because the very laws of physics that might provide resistance would be swept away and replaced by the different physical laws governing the true vacuum state. Within the expanding bubble of true vacuum, the fundamental constants of nature would take on new values determined by the deeper minimum of the potential energy landscape. The mass of the electron might change, altering the size of atoms and the chemistry of matter. The fine structure constant that governs electromagnetic interactions could shift, changing how charged particles interact with light. The masses of quarks might be modified, potentially destabilizing the protons and neutrons that form atomic nuclei. These changes would not occur gradually, allowing matter to adapt to new conditions. Instead, the boundary of the vacuum bubble would sweep through space at nearly the speed of light, instantly transforming the physics of any region it encounters. Stars, planets, galaxies, and all the complex structures of the universe would find themselves suddenly operating under completely different physical laws, likely leading to their immediate dissolution or transformation into entirely new forms of matter. The wavefront of vacuum decay would be invisible and undetectable until the moment it arrives. Unlike electromagnetic radiation or gravitational waves that travel at the speed of light and could theoretically be observed in advance, the expanding bubble of true vacuum carries no signal ahead of itself. The first indication of its approach would be the moment of its arrival, when the familiar laws of physics suddenly cease to apply and are replaced by an alien set of rules governing matter and energy. From the perspective of observers within the false vacuum, the universe would continue to appear completely normal right up until the instant of their annihilation. Stars would shine, planets would orbit, and life could continue to evolve and flourish, entirely unaware that somewhere in the cosmic distance, a bubble of true vacuum might be expanding toward them at nearly the speed of light. The vacuum decay front would be racing across intergalactic space, consuming galaxy after galaxy in its inexorable advance toward regions that remain blissfully ignorant of the approaching transformation. The internal structure of the true vacuum region would depend on the specific details of the quantum field potential, but it would likely be incompatible with the complex chemistry and nuclear physics that make current forms of matter possible. If the true vacuum state corresponds to significantly different particle masses or force strengths, atoms as we know them might not be able to exist. The delicate balance of electromagnetic and nuclear forces that allows for stable nuclei and chemical bonding could be completely disrupted. In some scenarios, the true vacuum might correspond to a state where the Higgs field takes on a much larger value, making all particles extremely massive and fundamentally altering the scale of atomic and molecular interactions. In other possibilities, the true vacuum might reduce particle masses so dramatically that matter becomes unable to form stable structures. The specific outcome would depend on the precise shape of the quantum field potential in regions we have never experimentally explored. Remarkably, multiple vacuum decay bubbles could form independently in different regions of space, each expanding at nearly the speed of light until they eventually meet and merge. The collision between expanding bubbles of true vacuum would create complex interference patterns and energy releases, but the ultimate results would be the same: the complete conversion of false vacuum to true vacuum throughout the affected regions. The timeline for vacuum decay is fundamentally unpredictable because it depends on quantum tunneling, an inherently probabilistic process. The transition from false vacuum to true vacuum could occur tomorrow, in a billion years, or never at all if the vacuum is actually stable rather than metastable. Physicists can calculate the probability of vacuum decay occurring within a given time period, but they cannot predict when or where such an event might actually happen. Current estimates based on our understanding of the Higgs field suggest that if the vacuum is indeed metastable, the typical timescale for decay could be incredibly long, perhaps 10 to the power of 100 years or more under normal conditions. This would make vacuum decay an extremely rare event, far less likely than other cosmic endings such as heat death or the Big Rip. But the probabilistic nature of quantum mechanics means that early decay remains a genuine possibility, however remote. The probability of vacuum decay could be enhanced by high-energy events that provide additional energy to push the Higgs field closer to the energy barrier separating false vacuum from true vacuum. Cosmic ray collisions, black hole evaporation, or hypothetical future particle accelerator experiments that probe extreme energy scales could potentially trigger vacuum decay if the field exists near the boundary of stability. This possibility has led to discussions about the cosmic responsibility of high-energy physics research. If our vacuum is metastable, experiments that create conditions of extreme energy density could potentially nucleate vacuum decay bubbles, though current calculations suggest that natural cosmic ray events routinely create far more extreme conditions than any conceivable human experiment. The fact that the universe has survived billions of years of cosmic ray bombardment provides some reassurance about vacuum stability. Vacuum decay represents a unique form of cosmic ending because it would not just destroy existing structures, but fundamentally rewrite the rules of physics itself. Unlike heat death, which represents the gradual approach to thermal equilibrium within our current physical laws, or the Big Rip, which pushes expansion beyond the limits of structural stability, vacuum decay would replace our entire framework of physical reality with something potentially unrecognizable. The philosophical implications of vacuum decay are profound. It suggests that even the most fundamental aspects of reality, the basic constants and forces that we consider unchanging, might themselves be contingent rather than absolute. The universe we observe, with its specific particle masses, force strengths, and physical laws, would represent just one possible realization among many potential physical realities, distinguished only by the accident of which vacuum state happened to be accessible during cosmic evolution. From a certain perspective, vacuum decay offers a form of cosmic renewal that other ending scenarios lack. While heat death leads to maximum entropy and the Big Rip to complete dissolution, vacuum decay would create entirely new possibilities for structure and complexity. The true vacuum state might support forms of matter and energy completely alien to our current experience, potentially giving rise to new types of complexity that we cannot currently imagine. Some speculative theories suggest that vacuum decay might not lead to a completely sterile universe, but could instead create conditions favorable for entirely different forms of physical organization. If the true vacuum supports stable particles and forces, even if they differ dramatically from our current physics, it might allow for the emergence of new types of structures, new forms of chemistry, and perhaps even new varieties of complexity and organization. The possibility of vacuum decay also raises questions about the nature of cosmic evolution and the role of stability in physical law. Our universe's apparent stability, which has allowed for billions of years of consistent physical behavior, might be an illusion sustained only by our limited perspective. The constants of nature that seem so solid and reliable might actually be balanced on a knife's edge, maintained only by the fact that no sufficiently large quantum fluctuation has yet pushed them over the threshold into a different state. Current research in theoretical physics continues to refine our understanding of vacuum stability, using increasingly sophisticated calculations to determine whether the Higgs field and other fundamental fields exist in stable or metastable configurations. These investigations combine quantum field theory, particle physics phenomenology, and cosmological observations to constrain the shape of field potentials at energy scales far beyond direct experimental reach. The discovery of additional fundamental particles or forces could dramatically alter the vacuum stability question. New physics beyond the standard model might provide additional contributions to field potentials, potentially stabilizing configurations that currently appear metastable or destabilizing states that seem secure. The ultimate resolution of the vacuum decay question may require experimental discoveries that extend our understanding of physics into previously unexplored energy ranges. Vacuum decay stands as perhaps the most fundamental of all cosmic ending scenarios, because it questions the permanence of physical law itself. While other possibilities work within our current understanding of physics to project how known forces and processes might evolve over cosmic time, vacuum decay suggests that our entire framework of physical understanding might be built on unstable foundations. The scenario serves as a reminder of the provisional nature of scientific knowledge and the possibility that even our most basic assumptions about reality might require revision. The vacuum of space, which appears empty and featureless, might actually harbor the potential for the most dramatic transformation imaginable, the complete replacement of one set of physical laws with another, fundamentally different system of natural behavior. In contemplating vacuum decay, we confront the ultimate questions about the nature of existence itself. Is our universe a stable, permanent reality governed by unchanging laws, or is it a temporary phase in a larger landscape of possible physical realities? The answer to this question will determine not just the ultimate fate of all matter and energy, but the very meaning of stability, permanence, and physical law in the deepest foundations of cosmic existence. Whether or not vacuum decay represents our universe's actual destiny, it provides a profound perspective on the nature of reality itself. It reminds us that even the most fundamental aspects of existence, the basic rules that govern matter and energy, might themselves be subject to change through processes we are only beginning to understand. In the end, vacuum decay represents not just a possible cosmic ending, but a gateway to entirely new forms of existence that challenge our most basic assumptions about the nature of physical reality. Big Bounce. Among the various visions of cosmic destiny, there exists a scenario that offers something rarely found in discussions of universal endings: genuine renewal. This is the Big Bounce, a model that suggests our universe may not be heading toward any final state at all, but rather participating in an eternal cycle of expansion and contraction, death and rebirth, where each cosmic epoch emerges from the ashes of its predecessor in an endless rhythm of cosmological resurrection. The Big Bounce represents a fundamental reimagining of cosmic history and destiny. Where the standard Big Bang model begins with a singular moment of creation from an initial state of infinite density and temperature, the Big Bounce proposes that this apparent beginning was actually a transition point, a cosmic turning point, where a previous universe that had been contracting reverse direction and began the expansion we observe today. Our Big Bang, in this view, was actually a big bounce, the moment when contraction became expansion in an eternal cosmic cycle. This elegant concept addresses one of the most profound puzzles in cosmology, the singularity problem. In traditional Big Bang cosmology, the universe emerges from a mathematical point where density and temperature become infinite and the laws of physics break down completely. This singularity represents a fundamental limitation in our understanding, a place where scientific description fails and mystery begins. The Big Bounce offers a solution by replacing the singular beginning with a smooth transition from a previous cosmic cycle. The theoretical foundations of the Big Bounce rest on modifications to Einstein's general relativity that become important under conditions of extreme density and curvature. While classical general relativity predicts that gravitational collapse must lead inevitably to singularities, quantum effects and alternative theories of gravity suggest that nature might possess mechanisms to prevent such breakdowns in physical law. These quantum gravitational effects would become dominant at densities approaching the Planck scale, creating a kind of cosmic cushion that prevents complete collapse. Loop quantum cosmology provides one of the most detailed frameworks for understanding how a Big Bounce might occur. This approach treats spacetime itself as quantized at the smallest scales, composed of discrete units rather than being perfectly continuous. When matter and energy are compressed to extraordinary densities, these quantum effects create a repulsive force that opposes further contraction, much like the incompressibility of matter, prevents atoms from being squeezed into arbitrarily small volumes. The transition through a Big Bounce would be one of the most remarkable events conceivable in physics. As a contracting universe approaches maximum compression, conventional matter would be crushed beyond recognition, with atoms dissolved into their constituent particles, and even atomic nuclei broken down into fundamental components. Temperatures would soar to levels that make stellar cores seem cold by comparison, and the entire observable universe would be compressed into a region smaller than a single atom. Yet, at the moment of maximum compression, quantum gravitational effects would assert themselves, creating a cosmic spring that reverses the contraction and initiates a new phase of expansion. The universe would literally bounce, transitioning from compression to expansion in a process that might unfold over time, scales far shorter than any directly observable phenomenon. The bounce itself could occur in a tiny fraction of a second, transforming cosmic collapse into cosmic expansion with extraordinary rapidity. The emerging universe that follows the bounce would initially be incredibly hot and dense, filled with elementary particles and radiation in conditions similar to those described in conventional Big Bang cosmology. But there would be subtle differences, signatures of the bounce process that might be detectable in the cosmic microwave background radiation or other observational probes. These differences would carry information about the previous cosmic cycle, providing a potential window into the universe's pre-bounce history. One of the most intriguing aspects of Big Bounce cosmology is its implications for cosmic memory and information transfer between cycles. Unlike scenarios where the universe ends in heat death or is destroyed in a big rip, the Big Bounce suggests that some information about previous cosmic epochs might survive the transition and influence the evolution of subsequent cycles. The quantum state of fields during the bounce could preserve certain characteristics of the preceding universe, creating a form of cosmic heredity that links different cycles together. The scale and timeline of Big Bounce cycles depend on the specific mechanisms driving the process, but many models suggest cycle lengths measured in hundreds of billions or even trillions of years. Each cycle would begin with rapid expansion similar to cosmic inflation, followed by a long period of matter-dominated evolution, where galaxies, stars, and complex structures can form and evolve. Eventually, the expansion would slow and reverse, leading to a phase of contraction that culminates in another bounce and the beginning of a new cycle. During the expansion phase of each cycle, cosmic evolution would proceed much as we observe in our current universe. Stars would form from collapsing gas clouds, nuclear fusion would create heavy elements, planets would coalesce from stellar debris, and complex chemistry would become possible. Life might emerge and evolve, civilizations could develop, and conscious beings might contemplate their cosmic situation much as we do today. Each cycle would provide billions of years for the full flowering of cosmic complexity. But the expansion phase would be temporary. Eventually, the gravitational attraction of matter would overcome the initial expansion, causing the universe to reach a maximum size and begin contracting. This turnaround might occur hundreds of billions of years in the future, long after our sun has died and our galaxy has merged with others. But it would be as inevitable as the bounce that initiated the cycle. The contraction phase would initially proceed slowly, with galaxies gradually approaching each other as space shrinks. For most of the contraction period, the changes would be barely perceptible, much like the early stages of expansion are nearly imperceptible from our current perspective. Stars would continue to shine, planets would maintain their orbits, and the basic structure of cosmic organization would remain intact. Only in the final stages of contraction would the effects become dramatic. As the universe shrinks to a small fraction of its maximum size, galaxies would merge and stellar systems would be disrupted by increasingly strong gravitational fields. The cosmic microwave background would heat up as the universe compresses, eventually becoming hot enough to affect stellar evolution and planetary environments. In the ultimate phase of contraction, all matter would be compressed into conditions of extreme density and temperature, setting the stage for another bounce. The Big Bounce scenario raises fascinating questions about the uniqueness and significance of our current cosmic epoch. If the universe undergoes endless cycles of expansion and contraction, our current phase represents just one chapter in an infinite cosmic story. The galaxies we observe, the stars that illuminate our night sky, and even the fundamental particles that compose our bodies would be temporary arrangements in an eternal dance of cosmic recycling. Yet each cycle would also be unique, shaped by quantum fluctuations during the bounce process and the specific conditions inherited from the previous cycle. While the broad outlines of cosmic evolution might repeat, the detailed structures and events of each cycle could be entirely different. Our universe, with its particular arrangement of galaxies and its specific evolutionary history, might represent a completely unique realization among the infinite sequence of cosmic cycles. Some versions of Big Bounce cosmology suggest that cycles might evolve over time, with each bounce slightly different from the last, due to the accumulation of quantum effects or changes in the fundamental parameters of physics. These evolutionary models propose that the universe might gradually change its character over many cycles, perhaps exploring different physical regimes or developing new forms of complexity that were impossible in earlier epochs. The possibility of cyclic evolution raises profound questions about cosmic purpose and direction. If each cycle builds upon the achievements of its predecessors, the eternal sequence of bounces might represent a form of cosmic learning or development, where the universe gradually explores the full range of possible structures and behaviors. Alternatively, the cycles might be truly repetitive, with each bounce returning the universe to essentially the same initial conditions and leading to similar evolutionary outcomes. Current observational evidence provides limited constraints on Big Bounce models, though several lines of investigation might eventually distinguish between cyclic and non-cyclic cosmologies. The cosmic microwave background radiation carries detailed information about the very early universe, and precision measurements of its properties might reveal signatures of pre-bounce physics. Gravitational wave detectors could potentially observe primordial gravitational waves generated during the bounce process, providing direct evidence for cyclic cosmology. The study of dark energy also bears on the viability of Big Bounce scenarios. If dark energy continues to accelerate cosmic expansion indefinitely, the universe might never reach the turnaround point necessary for contraction and bouncing. However, some models suggest that dark energy might evolve over cosmic time, potentially weakening or even reversing its effects on sufficiently long timescales. The ultimate behavior of dark energy over periods much longer than the current age of the universe remains one of the key uncertainties in cosmic evolution. Quantum gravity research continues to refine our understanding of how matter and space-time behave under conditions of extreme density and curvature. Loop quantum gravity, string theory, and other approaches to quantum gravity all suggest that classical general relativity must be modified at very high energies. But they differ in their specific predictions about bounce dynamics and the transfer of information between cycles. The Big Bounce also intersects with questions about the arrow of time and the nature of temporal flow in cyclic universes. If the universe undergoes endless cycles of expansion and contraction, what determines the direction of time within each cycle? Some models suggest that time might reverse during the contraction phase, leading to cycles where cause and effect relationships are inverted. Others propose that time always flows in the same direction, with each bounce representing a genuine temporal discontinuity. From a philosophical perspective, the Big Bounce offers a vision of cosmic existence that emphasizes renewal and continuity rather than ultimate endings. Where other scenarios lead to final states of equilibrium, dissolution, or transformation, the Big Bounce suggests that cosmic death is always followed by cosmic rebirth. This cyclical vision resonates with ancient philosophical and religious traditions that see time as circular rather than linear. But it emerges from modern physics rather than metaphysical speculation. The implications for life and consciousness in a bouncing universe are particularly intriguing. If cycles are long enough to allow for the full evolution of complexity, each bounce could give rise to new forms of life and intelligence that might develop completely different understandings of cosmic existence. These hypothetical beings might face the same questions about their universe's ultimate fate that we contemplate today, perhaps developing their own theories about cosmic cycles and bounces. Some speculative models suggest that advanced civilizations might even be able to influence the bounce process, potentially controlling or modifying the transition between cycles. If quantum effects during the bounce are sensitive to the prior state of matter and fields, sufficiently advanced technology might be able to encode information in ways that survive the bounce and influence the subsequent cycle. This raises the extraordinary possibility of communication or influence across cosmic cycles, linking different epochs of universal evolution. The Big Bounce stands out among cosmic ending scenarios because it denies the very concept of ultimate endings. Instead of leading to final states of heat death, collapse, or dissolution, it proposes that every cosmic death contains the seeds of cosmic rebirth. Each phase of expansion and structure formation is temporary, but it is followed by another phase that offers new opportunities for complexity and organization. This cyclical perspective fundamentally changes how we might think about cosmic purpose and meaning. If the universe undergoes endless cycles of death and rebirth, the significance of any particular cycle might seem diminished, but the eternal nature of the process might suggest a deeper form of cosmic purpose. The universe, in this view, is not evolving toward any final goal, but is instead engaged in an endless exploration of its own possibilities. Whether or not the Big Bounce represents our universe's actual behavior, it provides a powerful counterpoint to models that emphasize finality and termination. It reminds us that our current understanding of cosmic evolution remains incomplete, and that the universe might possess resources for renewal and regeneration that we have not yet fully appreciated. In the endless rhythm of expansion and contraction, death and rebirth, the Big Bounce offers a vision of cosmic existence that is both eternal and ever-changing, familiar yet endlessly renewable. The concept challenges our assumptions about beginnings and endings, suggesting that these might be human constructs that don't apply to the universe as a whole. In the Big Bounce scenario, every ending is also a beginning, every death a birth, and every conclusion the start of a new cosmic adventure. It presents the universe not as a story with a beginning, middle, and end, but as an eternal poem that writes and rewrites itself through the endless cycle of cosmic seasons, each bounce a new verse in an infinite composition of space, time, matter, and energy. Cyclic universe, Ekpyrotic model. Beyond the familiar three dimensions of space and the single dimension of time that define our everyday experience, lies a theoretical landscape of extraordinary richness and complexity. It is here, in the realm of higher dimensional physics and string theory, that we encounter one of the most elegant and ambitious attempts to understand cosmic cycles. the Ekpyrotic model. This sophisticated framework suggests that our universe participates in an endless dance with parallel realities, where cosmic history unfolds through the periodic collision of entire dimensional spaces, each encounter giving birth to a new cycle of cosmic evolution. The Ekpyrotic model, whose name derives from the ancient Greek word meaning out of fire, represents a profound synthesis of modern theoretical physics. It emerges from string theory, the ambitious framework that attempts to describe all fundamental forces and particles as vibrations of infinitesimally small strings existing in spaces with more than the 4 dimensions we directly experience. In this theoretical landscape, our observable universe would be confined to a 4-dimensional surface called a brane, floating within a higher dimensional space known as the bulk. This higher dimensional perspective fundamentally transforms our understanding of cosmic architecture, where conventional cosmology treats our universe as the entirety of physical reality. The Ekpyrotic model suggests that we inhabit just one of potentially many such branes, separated by microscopic distances, in dimensions we cannot directly perceive. These parallel branes would exist in the same higher dimensional space, each potentially harboring its own physics, its own matter and energy, and its own evolutionary history. The central mechanism driving cosmic cycles in the Ekpyrotic model involves the collision between our brane and a nearby parallel brane. These vast dimensional surfaces, each containing the equivalent of an entire universe, would slowly approach each other through the higher dimensional bulk space, drawn together by gravitational and other fundamental forces operating across the extra dimensions. The collision between such branes would release enormous amounts of energy, creating the hot, dense conditions that we associate with the Big Bang. But in the Ekpyrotic framework, this collision would not represent a singular moment of creation. Instead, it would be just one event in an endless sequence of brane collisions, each separated by periods lasting perhaps trillions of years. Between collisions, the branes would separate and evolve independently, allowing time for matter to cool, galaxies to form, stars to shine, and complex structures to emerge. Eventually, the attractive forces operating through the bulk would draw the branes together once again, leading to another collision and the beginning of a new cosmic cycle. The approach toward each collision would unfold over cosmic timescales that dwarf the current age of our universe. Initially, the parallel brane would be separated from ours by distances measured in the higher dimensional bulk, making its influence barely detectable even through the most sensitive gravitational measurements. The extra-dimensional space between the branes would appear empty and featureless, filled only with the quantum fluctuations that permeate all of space-time. As the branes slowly approach each other, their gravitational interaction would begin to affect the evolution of matter and fields on each surface. The parallel brane's gravity would create subtle distortions in space-time that might manifest as modifications to cosmic expansion or changes in the behavior of dark energy. These effects would be incredibly difficult to detect, requiring precision measurements of cosmic distances and expansion rates over periods much longer than human civilization has existed. The actual collision between branes would represent one of the most energetic events conceivable in physics. When two 4-dimensional surfaces containing the mass energy equivalent of entire universes come into contact, the result would be the sudden conversion of kinetic energy into radiation and particles on a truly cosmic scale. The collision would heat both branes to temperatures far exceeding those in stellar cores, creating conditions similar to those predicted for the first moments after the Big Bang. During the collision, the boundary between the two branes would become a region of extraordinary physics, where the normal rules governing matter and energy might temporarily cease to apply. Particles and fields from both branes would interact in ways impossible under normal circumstances, potentially creating exotic forms of matter or triggering phase transitions in the fundamental forces. The collision zone would be a crucible where new physics emerges from the meeting of previously separate realities. The energy released during brane collision would spread across both surfaces like ripples on cosmic ponds, but these would be ripples of space-time itself, carrying temperatures and energies that transform everything they encounter. Matter that had existed in stable configurations for billions of years would be instantly vaporized and converted into its most fundamental components. The the complex chemistry that enables planets and life would be reduced to elementary particles moving at relativistic speeds through a sea of intense radiation. Yet, from this cosmic destruction would emerge the seeds of new creation. The hot, dense conditions created by brane collision would be ideal for the processes that create matter from energy and establish the initial conditions for cosmic evolution. As the collision energy spreads and dilutes across the brane surfaces, temperatures would drop and allow for the formation of new particles, the synthesis of light elements, and the establishment of the physical laws that will govern the next cosmic cycle. The post-collision evolution would initially proceed much like conventional Big Bang cosmology, with periods of rapid expansion, nucleosynthesis, and the gradual cooling that allows for the formation of atoms and the decoupling of matter from radiation. But the Ekpyrotic model predicts subtle differences in this evolution, signatures of the collision process that might be detectable in the cosmic microwave background or other observational probes of the early universe. One of the most remarkable features of the Ekpyrotic model is its potential to solve several outstanding problems in cosmology through the collision mechanism. The flatness problem, which asks why the universe appears to have exactly the critical density needed to avoid either immediate collapse or runaway expansion, could be resolved if brane collisions naturally produce flat geometries. The horizon problem, concerning how widely separated regions of the universe came to have the same temperature, might be explained by the mixing of fields during collision events. The model also offers a natural explanation for dark matter through the physics of extra dimensions. Particles confined to the parallel brane would interact gravitationally with matter on our brane but would be otherwise invisible, creating the kind of missing mass that we attribute to dark matter. The collision process might even transfer some dark matter between branes, creating complex patterns of invisible matter that influence cosmic structure formation. Between collisions, each brane would undergo its own independent evolution, potentially developing completely different physical characteristics and evolutionary pathways. The parallel brane might have different fundamental constants, alternative particle physics, or even different numbers of spatial dimensions within its surface. These variations would create a kind of cosmic diversity where each cycle explores different possibilities for physical law and cosmic organization. The separation phase following each collision would involve the gradual movement of branes away from each other through the bulk space. This separation would be driven by the same collision energy that heated the branes, but channeled into expansion through the extra dimensions rather than within the familiar 3 dimensions of space. As the branes separate, their gravitational influence on each other would weaken, allowing each to evolve according to its own internal dynamics. During the long separation periods, lasting perhaps hundreds of billions or even trillions of years, cosmic evolution would proceed independently on each brane. Stars would form and die, galaxies would merge and evolve, and complex structures might emerge and flourish. Life could arise and develop into forms of intelligence capable of contemplating their cosmic situation, much as we do today. These civilizations would observe their universe's expansion and might even detect subtle signatures of the parallel brane through precision gravitational measurements. The duration of each cycle would depend on the specific mechanisms driving brane motion through the bulk. Some models suggest that additional fields or forces operating in the extra dimensions could accelerate or decelerate the approach toward collision, creating cycles of varying length. Others propose that quantum effects in the bulk might introduce randomness into the collision timing, making each cycle unpredictably different from its predecessors. The question of information transfer between cycles becomes particularly intriguing in the Ekpyrotic framework. Unlike models where the universe undergoes complete destruction and recreation, brane collisions might preserve certain types of information in the form of field configurations or topological structures that survive the collision process. Advanced civilizations might even be able to encode messages in forms that could survive brane collision and influence the evolution of subsequent cycles. The parallel brane itself represents a fascinating philosophical puzzle. If it contains matter and energy equivalent to an entire universe, it might harbor its own forms of complexity, its own versions of galaxies and stars, and perhaps even its own forms of life and intelligence. These hypothetical beings would exist in a reality fundamentally parallel to our own, separated by microscopic distances in dimensions we cannot perceive, yet sharing the same cosmic destiny of endless collision and separation. Current observational cosmology provides limited direct evidence for the Ekpyrotic model, though several predictions might eventually be testable. The model makes specific predictions about the spectrum of primordial gravitational waves and the statistical properties of cosmic microwave background fluctuations that differ from those of conventional inflation theory. Future gravitational wave detectors and cosmic microwave background missions might be sensitive enough to distinguish between these scenarios. String theory research continues to develop the theoretical foundations for brane cosmology and collision dynamics. The mathematics of higher dimensional gravity, the physics of brane interactions, and the mechanisms for energy transfer during collisions remain active areas of investigation. These studies are gradually refining our understanding of how brane worlds might behave and what observational signatures they might produce. The Ekpyrotic model also connects to broader questions about the landscape of possible universes predicted by string theory. If the theory allows for vast numbers of different vacuum states, each corresponding to different physical laws and particle spectra, brane collisions might provide a mechanism for exploring this landscape. Each collision might result in slightly different physics for the subsequent cycle, allowing the universe to sample different regions of the theoretical possibility space. Laboratory experiments in high-energy particle physics might eventually provide indirect evidence for extra dimensions and brane physics through the discovery of new particles or forces that behave according to higher dimensional physics. The Large Hadron Collider and future particle accelerators probe energy scales where extra-dimensional effects might become detectable, potentially providing evidence for the theoretical framework underlying Ekpyrotic cosmology. The model's implications for cosmic fine-tuning are particularly intriguing. If physical constants and laws can change between collision cycles, the Ekpyrotic universe provides a natural mechanism for exploring different parameter combinations. Our current universe, with its apparently fine-tuned physical constants that allow for complex chemistry and stable stellar evolution, might represent just one realization among countless others, sampled through the endless sequence of brane collisions. From the perspective of consciousness and cosmic purpose, the Ekpyrotic model suggests a universe engaged in endless experimentation with its own possibilities. Each collision cycle represents a new attempt at cosmic organization, a fresh exploration of how matter and energy can be arranged to create complexity and structure. Life and intelligence, when they arise, become part of this cosmic experiment, temporary expressions of the universe's capacity for self-organization and self-awareness. The cyclical nature of Ekpyrotic cosmology also raises profound questions about the nature of progress and development in cosmic evolution. If each cycle offers billions of years for the emergence of complexity and consciousness, but then erases these achievements through brane collision, what meaning can we assign to cosmic development? Perhaps the meaning lies not in permanent achievement, but in the endless capacity for renewal and exploration. Advanced civilizations in an Ekpyrotic universe would face unique challenges and opportunities. Knowing that their cosmic epoch was temporary, they might focus on understanding the collision process and perhaps even influencing it to preserve information or structures across cycles. The approach of the next collision would be simultaneously a cosmic death sentence and an opportunity for transformation into something entirely new. The Ekpyrotic model represents one of the most sophisticated attempts to understand cosmic cycles within the framework of modern theoretical physics. It combines insights from string theory, higher dimensional gravity, and observational cosmology to create a vision of cosmic evolution that is both elegant and incredibly complex. While much of the model remains speculative, it provides a concrete framework for thinking about how our universe might participate in processes operating on scales far beyond our direct experience. In the endless dance of brane collision and separation, the Ekpyrotic universe offers a vision of cosmic existence that emphasizes both destruction and creation, ending and beginning, familiar physics and exotic possibilities. Each collision represents both the death of existing structures and the birth of new realities, while each separation period allows for the full flowering of cosmic complexity before the cycle begins anew. The model reminds us that our universe might be part of a much larger and more complex reality than we can directly observe. The 3 dimensions of space and 1 dimension of time that define our immediate experience might be just a small subset of a higher dimensional arena where cosmic evolution unfolds through mechanisms we are only beginning to understand. In this grander perspective, our cosmic story becomes part of an even greater narrative of dimensional collision and separation, played out on scales and through processes that challenge our most fundamental assumptions about the nature of reality itself. Boltzmann brain dominance. In the vast expanse of cosmic time, when the last stars have flickered out and the universe has grown cold and dark, there emerges one of the most profound and unsettling concepts in all of cosmology. It challenges our very understanding of consciousness, reality, and what it means to exist. This is the realm of Boltzmann brains, named after the Austrian physicist Ludwig Boltzmann, who first glimpsed the statistical foundations that would lead to this extraordinary idea. To understand Boltzmann brain dominance, we must first journey back to the fundamental nature of entropy and thermodynamics. Entropy, in its simplest form, is a measure of disorder in a system. The second law of thermodynamics tells us that entropy always increases over time in an isolated system. This means that the universe is constantly moving from states of order to states of disorder, from hot to cold, from organized to chaotic. But here lies a fascinating paradox that Boltzmann himself wrestled with. If entropy always increases, how did we arrive at the highly ordered state we observe today? How did stars form, galaxies cluster, and complex structures like planets and life emerge from what should have been an increasingly disordered cosmos? Boltzmann proposed that these ordered states are simply statistical fluctuations in an otherwise random system. Like waves occasionally forming patterns on a chaotic sea, our ordered universe is merely a temporary deviation from equilibrium. This statistical interpretation of thermodynamics leads us to a startling realization about the far future of our cosmos. In the deep future, trillions upon trillions of years from now, the universe will have reached what physicists call thermal equilibrium. All the stars will have burned out, black holes will have evaporated through Hawking radiation, and space will be filled with nothing but elementary particles at an incredibly low temperature, just barely above absolute zero. In this seemingly dead universe, quantum mechanics tells us that particles will still undergo random fluctuations. Most of these fluctuations will be tiny and meaningless, but occasionally, purely by chance, larger fluctuations will occur. These random quantum events might spontaneously create small pockets of order within the vast sea of equilibrium. A few particles might randomly arrange themselves into a brief pattern before quickly dissolving back into chaos. Now comes the truly mind-bending part. Among all the possible fluctuations that could occur in this far future universe, some might be large enough and complex enough to create functioning brains. These would be Boltzmann brains, conscious entities that spontaneously emerge from random quantum fluctuations, complete with memories, thoughts, and experiences that feel entirely real to them. The mathematics behind this concept is both elegant and terrifying. In an infinite or extremely long-lived universe at thermal equilibrium, every possible configuration of matter that doesn't violate the laws of physics will eventually occur, and will occur infinitely many times. This includes configurations that form conscious brains with false memories of entire lives and civilizations that never actually existed. What makes this scenario so profound is the question of probability. If the universe continues for an extremely long time, which outcome is more likely? That conscious observers like ourselves evolved naturally through billions of years of cosmic evolution, or that we are actually Boltzmann brains that randomly fluctuated into existence just moments ago, complete with false memories of our entire past. The disturbing answer, according to the mathematics, is that Boltzmann brains would vastly outnumber naturally evolved conscious beings. For every real observer that emerged through the slow process of stellar formation, planet formation, and biological evolution, there would be countless trillions of Boltzmann brains that randomly popped into existence in the far future, each convinced that their false memories represent real experiences. This creates what philosophers and physicists call the Boltzmann brain paradox. If Boltzmann brains are more numerous than naturally evolved observers, then statistically speaking, you are more likely to be a Boltzmann brain than a real person. The memories you have of your childhood, your education, your relationships, even your understanding of physics and cosmology, would all be random configurations of neural activity that happened to fluctuate into existence just now. The implications of this scenario extend far beyond mere philosophical speculation. If Boltzmann brain dominance is correct, it fundamentally undermines our ability to trust scientific knowledge itself. How can we have confidence in our theories about the universe if we might be random fluctuations with false memories of learning those theories? How can we trust our observations and experiments if our entire scientific history might be nothing more than randomly generated neural patterns? Some physicists have argued that the Boltzmann brain paradox represents a reductio ad absurdum, a proof by contradiction that our current cosmological models must be incomplete or incorrect. If a theory predicts that we are most likely random fluctuations rather than evolved beings, perhaps that theory needs to be revised. This has led to various proposals for avoiding the Boltzmann brain problem. One approach is to invoke the anthropic principle, the idea that we observe the universe to be suitable for life because we exist to observe it. In this view, even if Boltzmann brains are more numerous overall, they are less likely to make reliable observations about the universe. A naturally evolved observer has a long evolutionary history that has fine-tuned their sensory and cognitive systems to accurately perceive reality. A Boltzmann brain, on the other hand, is just a random fluctuation that happens to have the pattern of a brain, but has no guarantee that its perceptions correspond to anything real. Another proposed solution involves reconsidering the ultimate fate of the universe itself. If the universe doesn't continue forever in thermal equilibrium, but instead ends in a big rip, a big crunch, or some other finite scenario, then there might not be enough time for significant numbers of Boltzmann brains to form. The balance between naturally evolved observers and random fluctuations would tip decisively in favor of the evolved observers. Some cosmologists have also suggested that the vacuum state of the universe might not be stable over extremely long time periods. If the quantum vacuum eventually decays into a lower energy state, this could reset the cosmic clock and prevent the formation of Boltzmann brains. Alternatively, if dark energy continues to accelerate the expansion of the universe, it might prevent the thermal equilibrium state that is necessary for Boltzmann brain formation. The concept of eternal inflation, where our observable universe is just one bubble in an infinite multiverse of expanding regions, also offers a potential escape from Boltzmann brain dominance. In eternal inflation models, new regions of space are constantly being created through inflationary processes. These newly created regions would be far from thermal equilibrium and would naturally give rise to stars, galaxies, and evolved life. If this process continues forever, naturally evolved observers might always outnumber Boltzmann brains, even in the far future. Yet another approach to the Boltzmann brain problem involves questioning our assumptions about consciousness itself. Perhaps consciousness is not simply a pattern of neural activity that can be randomly duplicated, but requires a specific evolutionary and developmental history. A true conscious experience might need to be embedded in a continuous causal chain that extends back through biological evolution and cosmic history. Random fluctuations, no matter how brain-like, might not possess genuine consciousness at all. The debate over Boltzmann brains also touches on deep questions about the nature of time and causality. In thermal equilibrium, there is no preferred direction of time, no clear distinction between past and future. A Boltzmann brain that randomly forms might have memories pointing toward the future, just as easily as memories pointing toward the past. This temporal symmetry raises questions about whether such entities could even be considered truly conscious in any meaningful sense. From a purely statistical standpoint, most Boltzmann brains would not be perfect duplicates of evolved brains. The vast majority would be barely conscious entities with confused, contradictory, or incomplete memories and sensory experiences. Only an infinitesimally small fraction would have coherent, consistent experiences that could be mistaken for those of a naturally evolved observer. This statistical reality provides some comfort, as it suggests that coherent observers like ourselves are more likely to be the product of genuine cosmic evolution rather than random fluctuation. The Boltzmann brain scenario also raises profound questions about personal identity and continuity of consciousness. If you were a Boltzmann brain, you would have no past and no future beyond the brief moment of your existence. Your entire sense of having lived a continuous life would be an illusion created by randomly arranged memories. Yet, from your subjective perspective, this illusion would be indistinguishable from reality. Some philosophers have argued that the Boltzmann brain paradox demonstrates the limits of purely statistical approaches to understanding consciousness and existence. They suggest that consciousness cannot be reduced to mere information patterns, but requires something more, perhaps related to the integrated information theory of consciousness or other approaches that emphasize the dynamic, process-based nature of conscious experience. The mathematical framework underlying Boltzmann brain dominance relies heavily on assumptions about probability and infinity that may not reflect the true nature of our universe. If the universe is finite in spatial extent or temporal duration, or if there are fundamental limits to the kinds of fluctuations that can occur, the Boltzmann brain problem might be avoided entirely. Some theories in quantum gravity suggest that space-time itself has a granular structure at the smallest scales, which could place constraints on the types of random fluctuations possible. Recent developments in cosmology have also brought new perspectives to the Boltzmann brain problem. The discovery of dark energy and the accelerating expansion of the universe has led to models where different regions of space become causally disconnected from each other. In such scenarios, the conditions necessary for thermal equilibrium might never be achieved on a global scale, preventing the formation of Boltzmann brains altogether. String theory and other approaches to quantum gravity have introduced the possibility of multiple dimensions and complex vacuum structures that could affect the long-term evolution of the universe. If our apparent three-dimensional space is actually embedded in a higher dimensional structure, the dynamics of thermal equilibrium and random fluctuations might be fundamentally different from what we expect based on conventional thermodynamics. The Boltzmann brain concept also intersects with ideas about the simulation, hypothesis, and computational theories of consciousness. If consciousness can arise from any sufficiently complex information processing system, then Boltzmann brains might be just one type of randomly occurring conscious entity. In a universe filled with quantum computers or other information processing systems, conscious experiences might spontaneously emerge from random computational processes as well as from random physical fluctuations. As we contemplate the possibility of Boltzmann brain dominance, we are forced to confront the deepest questions about the nature of reality, consciousness, and our place in the cosmic order. Are we the products of billions of years of stellar nucleosynthesis, planetary formation, and biological evolution? Or are we merely random fluctuations in an ancient cold universe, dreaming of a past that never was? The answer to this question may ultimately depend on discoveries we have yet to make about the fundamental nature of space, time, and consciousness itself. The beauty and terror of the Boltzmann brain scenario lies in its unfalsifiability. If you are a Boltzmann brain, there is no way to prove it, because all your evidence for being a naturally evolved observer is contained within your randomly generated memories. This epistemic limitation forces us to confront the boundaries of what we can know about our own existence and the nature of the universe we inhabit. The relationship between Boltzmann brains and other cosmological phenomena adds yet another layer of complexity to this already intricate scenario. Consider the role of vacuum fluctuations in quantum field theory. Even in empty space, the uncertainty principle ensures that particle-antiparticle pairs are constantly popping into existence and annihilating each other. These quantum fluctuations create a subtle but measurable energy density throughout the universe. In the far future thermal equilibrium state, these same quantum processes would be responsible for the formation of Boltzmann brains, but on a vastly larger and more complex scale. The energy requirements for creating a Boltzmann brain are enormous. A functioning brain requires billions of neurons arranged in precisely the right configuration, each with the correct electrochemical properties. The probability of such a configuration arising spontaneously is so incredibly small that it boggles the mind. Yet, in an infinite or extremely long-lived universe, even events with vanishingly small probabilities become inevitable. This is the strange mathematics of infinity at work, where impossible events become not just possible, but certain. Interestingly, the most likely type of Boltzmann brain would not be a perfect replica of a human brain, but rather the minimal conscious system capable of having experiences. This might be something like a simple observer moment, a brief flash of consciousness lasting only a fraction of a second, with just enough complexity to constitute genuine awareness. These minimal Boltzmann brains would vastly outnumber the more complex versions that might have elaborate false memories of entire lifetimes. The concept of Boltzmann brain dominance also intersects with questions about the multiverse and the anthropic principle in subtle ways. If our universe is part of a larger multiverse where different regions have different physical constants and laws of nature, then the probability calculations for Boltzmann brains become even more complex. Some regions of the multiverse might be more conducive to the formation of naturally evolved observers, while others might be dominated by random fluctuations. Recent research in cosmology has revealed that the expansion of our universe is accelerating due to dark energy. This acceleration has profound implications for the Boltzmann brain problem. As space expands faster and faster, regions of the universe become causally disconnected from each other. This process, known as cosmic inflation or eternal inflation, might prevent the universe from ever reaching the thermal equilibrium state necessary for Boltzmann brain formation. Instead of a single, thermally equilibrated universe, we might have an ever-expanding network of causally isolated regions, each too young and dynamic to support random conscious fluctuations. The philosophical implications of living in a universe potentially dominated by Boltzmann brains extend to questions about moral responsibility and the meaning of existence. If most conscious beings are random fluctuations with false memories, what does this mean for concepts like justice, love, creativity, and human achievement? Are the great works of art, literature, and science that we cherish merely random patterns mistaken for meaningful accomplishments? Or does their subjective reality to conscious observers, whether evolved or fluctuated, give them genuine significance? Some thinkers have proposed that the Boltzmann brain paradox might be resolved through a deeper understanding of consciousness itself. Perhaps consciousness is not simply an emergent property of complex information processing, but requires a specific type of causal history that cannot be randomly duplicated. This view suggests that genuine consciousness might be inherently tied to the process of evolution, development, and learning that occurs over extended periods of time. The timescales involved in Boltzmann brain formation are almost incomprehensibly vast. We are talking about periods so long that the age of our current universe, some 13.8 billion years, appears as merely the briefest instant in comparison. These are timescales where entire cycles of cosmic evolution, from Big Bang to heat death, could repeat countless times. In such temporal vastness, the distinction between reality and random fluctuation becomes increasingly difficult to maintain. Modern developments in quantum mechanics and information theory have also brought new perspectives to the Boltzmann brain problem. The concept of quantum decoherence, which explains how quantum systems lose their quantum properties and behave classically, might place constraints on the types of conscious systems that can form through random fluctuations. A Boltzmann brain would need to maintain quantum coherence in just the right way to support conscious experience, which might be much more difficult than simply arranging particles in brain-like patterns. Perhaps the most profound lesson of the Boltzmann brain paradox is that it reminds us of the extraordinary nature of our existence. Whether we are evolved beings or random fluctuations, the fact that consciousness exists at all, that the universe has given rise to entities capable of contemplating their own existence and the cosmos that contains them, remains one of the deepest mysteries in all of science and philosophy. In the vast darkness of the far future, whether populated by Boltzmann brains or empty of consciousness altogether, the very possibility of awareness, of thought, of the universe knowing itself through conscious observers stands as perhaps the most remarkable phenomenon in all of cosmic history. Proton decay and degenerate era. Beyond the age of stars and galaxies, beyond the time when black holes dominate the cosmos, there lies an epoch so distant and strange that it challenges our very conception of matter itself. This is the Degenerate era, a time when the universe will be populated not by the familiar atoms that make up everything we know, but by the slowly decaying remnants of what were once protons, the fundamental building blocks of all atomic nuclei. To understand this far future epoch, we must first journey into the heart of matter itself, to the level of subatomic particles and the forces that bind them together. The proton, one of the most familiar particles in physics, sits at the center of every atomic nucleus except hydrogen, where it stands alone. For over a century, physicists have considered the proton to be stable, essentially immortal on any timescale we could imagine. Yet, some of our most sophisticated theories suggest that even these fundamental particles may not last forever. The story begins with our understanding of the fundamental forces of nature. We know of 4 fundamental forces: gravity, electromagnetism, the strong nuclear force, and the weak nuclear force. The electromagnetic force governs the behavior of charged particles. The strong force holds atomic nuclei together. The weak force is responsible for certain types of radioactive decay. And gravity shapes the large-scale structure of the universe. For decades, physicists have sought to unify these forces into a single theoretical framework, a grand unified theory that would show how all forces are merely different manifestations of a single underlying force. Grand unified theories, or GUTs as they are known, make a startling prediction. Protons are not stable. According to these theories, given enough time, even protons will eventually decay into lighter particles. The predicted lifetime of a proton varies depending on the specific grand unified theory, but most estimates place it somewhere around 10 to the 34th power years. This is an almost incomprehensibly long time, far longer than the current age of the universe, which is only about 14 billion years, or 10 to the 10th power years. To put this timescale into perspective, imagine that the entire history of the universe from the Big Bang to the present day represents just 1 second. On this scale, the proton decay timescale would correspond to more than 10 trillion years. It is a span of time so vast that all the stars in the universe will have burned out. All the black holes will have evaporated through Hawking radiation, and the cosmos will have expanded and cooled to temperatures just barely above absolute zero. The mechanism by which protons might decay involves processes that violate one of the most cherished conservation laws in physics: the conservation of baryon number. Baryons are particles made up of 3 quarks, and protons are the lightest stable baryons. In all observed nuclear and particle physics processes, the total number of baryons minus antibaryons remains constant. But grand unified theories suggest that at extremely high energies or over extremely long time periods, this conservation law might be violated through the exchange of very massive particles called X bosons. When a proton decays, it doesn't simply disappear. Instead, it transforms into lighter particles, typically a positron and a neutral pion, which itself quickly decays into 2 gamma-ray photons. The positron, being the antiparticle of the electron, will quickly encounter an electron and annihilate, producing more gamma rays. The end result is that the mass of the proton is converted entirely into electromagnetic radiation and possibly neutrinos, depending on the specific decay mode. The experimental search for proton decay has been ongoing for decades, with physicists building ever more sensitive detectors deep underground to shield them from cosmic rays and other sources of background radiation. These experiments involve monitoring enormous tanks of pure water or other materials, watching for the telltale signs of proton decay. So far, no definitive evidence for proton decay has been found, which has allowed scientists to place lower bounds on the proton lifetime that are consistent with grand unified theory predictions. Now, let us journey forward in time to the epoch when proton decay begins to dominate the evolution of the universe. This is the Degenerate era, so named because ordinary matter as we know it will have largely disappeared, leaving behind a universe populated primarily by elementary particles, radiation, and the exotic remnants of stellar evolution. By the time we reach the Degenerate era, the universe will have undergone profound changes. All main sequence stars will have exhausted their nuclear fuel and evolved into white dwarfs, neutron stars, or black holes. The red dwarf stars, the smallest and longest-lived of all stars, will have finally burned out after trillions of years of steady hydrogen fusion. Galaxies will have merged and restructured themselves through gravitational interactions, and most of the remaining matter will be locked up in white dwarf stars and other stellar remnants. White dwarf stars represent one of the most important components of the Degenerate era universe. These are the compressed cores of dead stars, supported against gravitational collapse by electron degeneracy pressure, a quantum mechanical effect that prevents electrons from occupying the same quantum state. A typical white dwarf has about the mass of our Sun compressed into a volume roughly the size of Earth, making them incredibly dense objects with surface gravities hundreds of thousands of times stronger than Earth's. In the early phases of the Degenerate era, these white dwarfs will slowly cool and fade, radiating away their remaining thermal energy over periods of trillions of years. As they cool, they will transition through a sequence of colors, from white to yellow to red to infrared, eventually becoming cold, dark objects known as black dwarfs. These black dwarfs will represent the fossilized remains of stellar evolution, dense objects composed primarily of carbon and oxygen nuclei, surrounded by a sea of degenerate electrons. But even these seemingly eternal stellar remnants are not immune to the effects of proton decay. As protons within the carbon and oxygen nuclei begin to decay, the black dwarfs will slowly dissolve from within. Each proton decay event releases energy in the form of gamma rays and other particles, gradually heating the stellar remnant and causing it to expand. Over the vast timescales of the Degenerate era, entire black dwarf stars will essentially evaporate, their mass converted into radiation and elementary particles. The process of stellar remnant dissolution through proton decay occurs gradually over periods comparable to the proton lifetime itself. A black dwarf star might maintain its basic structure for 10 to the 34th power years, but eventually, the cumulative effect of countless proton decay events will overcome the degeneracy pressure that supports the star against gravitational collapse. The star will expand and ultimately disperse its remaining mass into space as a diffuse cloud of electrons, positrons, neutrinos, and electromagnetic radiation. Neutron stars, the even more exotic remnants of massive stellar explosions, face a similar fate during the Degenerate era, though their evolution is more complex. These objects are composed primarily of neutrons, which are themselves made up of quarks bound together by the strong nuclear force. While neutrons are normally unstable when isolated, decaying with a half-life of about 15 minutes, they can be stable when packed together at nuclear densities within a neutron star. However, grand unified theories predict that neutrons, like protons, should eventually decay through processes that violate baryon number conservation. The decay modes for neutrons might be different from those of protons, potentially producing different combinations of leptons and mesons, but the ultimate result is the same: the gradual dissolution of neutron star matter into elementary particles and radiation. The decay of neutron stars during the Degenerate era would be a spectacular process if there were any observers present to witness it. As neutrons decay within the ultra-dense stellar core, the star would gradually lose mass and the remaining matter would become less gravitationally bound. Eventually, the neutron star might expand dramatically, perhaps even exploding in a final burst of radiation, as the last vestiges of nuclear matter convert themselves into lighter particles. Brown dwarfs, the failed stars that never achieved sufficient mass to sustain nuclear fusion, also populate the Degenerate era universe. These objects, with masses between about 13 and 80 times that of Jupiter, are composed primarily of hydrogen and helium in various states of degeneracy. Like other forms of ordinary matter, brown dwarfs will eventually succumb to proton decay, though their evolution might be different from that of white dwarfs due to their different composition and internal structure. The planets and other solid bodies that survive into the Degenerate era will also experience the effects of proton decay. Rocky planets like Earth are composed primarily of silicon, oxygen, iron, and other elements whose nuclei contain numerous protons. Over the vast timescales of proton decay, these worlds will literally dissolve from within, their atoms breaking apart as protons decay into lighter particles. Mountains will crumble not through erosion or tectonic activity, but through the fundamental breakdown of the matter from which they are composed. Gas giant planets present an interesting case during the Degenerate era. These worlds are composed primarily of hydrogen and helium, the lightest elements in the periodic table. Hydrogen nuclei are simply individual protons, so the decay of these particles directly converts the bulk of the planet's mass into radiation and elementary particles. A gas giant planet might persist as a gravitationally bound system for much of the Degenerate era, slowly losing mass as its constituent protons decay one by one. The asteroid belts, comets, and other small bodies scattered throughout planetary systems will also gradually disappear during this epoch. These objects, composed of rock, ice, and various organic compounds, contain countless protons within their atomic nuclei. Over time, proton decay will cause even the smallest pebbles and ice crystals to disintegrate, leaving behind only elementary particles and electromagnetic radiation. One of the most profound aspects of the Degenerate era is the transformation of the cosmic environment itself. In our current epoch, space is filled with a thin but detectable gas of hydrogen and helium, the remnants of Big Bang nucleosynthesis and stellar processing. During the Degenerate era, this interstellar medium will slowly disappear as protons decay, leaving behind a much more tenuous gas of electrons, positrons, neutrinos, and photons. The magnetic fields that thread through galaxies and pervade interstellar space will also evolve during this epoch. These fields are maintained by electric currents flowing through ionized gas, and as the gas density decreases due to proton decay, the magnetic fields will gradually weaken and dissipate. This process will take place over timescales comparable to the proton decay time, fundamentally altering the electromagnetic environment of the universe. The cosmic microwave background radiation, the afterglow of the Big Bang that currently permeates all of space, will also undergo significant changes during the Degenerate era. By this time, the expansion of the universe will have redshifted this radiation to extremely long wavelengths and incredibly low temperatures. The additional photons produced by proton decay throughout the universe will add to this background, though their contribution will be spread over such vast volumes of space that their effect on the overall radiation density will be minimal. Dark matter, the mysterious substance that makes up about 27% of the universe's total mass energy, introduces additional complexity to the Degenerate era scenario. Current theories suggest that dark matter particles might also be unstable over extremely long timescales, potentially decaying into lighter particles or radiation. If dark matter particles have lifetimes comparable to or shorter than protons, they could significantly influence the evolution of the universe during this epoch. The decay of dark matter would have profound implications for the large-scale structure of the universe during the Degenerate era. Dark matter currently provides the gravitational scaffolding around which galaxies and galaxy clusters are organized. If this matter begins to decay, the gravitational binding of these structures would weaken, potentially leading to their gradual dissolution over cosmic time. Some theoretical models suggest that certain types of dark matter particles might decay into ordinary matter, effectively reversing the matter-antimatter asymmetry that characterized the early universe. This could lead to spectacular annihilation events as newly created antimatter encounters the remaining ordinary matter, producing bursts of gamma radiation that could briefly illuminate the otherwise dark Degenerate era cosmos. The role of quantum mechanics becomes increasingly important during the Degenerate era, as matter becomes more and more dilute due to proton decay. Quantum effects that are normally negligible begin to dominate the behavior of particles and fields. Quantum tunneling effects might allow particles to overcome energy barriers that would be insurmountable in classical physics, leading to unexpected chemical reactions and nuclear processes in the low-density environment of the far future. Vacuum fluctuations, the spontaneous creation and annihilation of particle-antiparticle pairs that occurs even in empty space, become relatively more significant as the density of real matter decreases. These quantum fluctuations create a subtle but measurable energy density throughout space, and in the extremely dilute environment of the Degenerate era, they might play an important role in determining the overall dynamics of cosmic evolution. The concept of entropy, the measure of disorder in a system, takes on special significance during the Degenerate era. As protons decay and convert organized matter into random radiation and elementary particles, the entropy of the universe continues to increase. This process represents a continuation of the cosmic trend toward greater disorder that began with the Big Bang and will ultimately lead to the heat death of the universe. However, the increase in entropy during the Degenerate era is not uniform throughout space. Local regions might experience temporary decreases in entropy due to gravitational effects or quantum fluctuations, leading to the formation of small-scale structures or ordered configurations of particles. These entropy fluctuations could potentially give rise to interesting phenomena, though they would be short-lived on cosmological timescales. The temperature of the universe during the Degenerate era will be extraordinarily low, potentially just a tiny fraction of a degree above absolute zero. At such temperatures, thermal motion becomes negligible, and quantum effects dominate the behavior of matter and energy. This extreme cold would freeze out most chemical reactions and nuclear processes, leaving proton decay as one of the few remaining sources of energy and activity in the cosmos. Despite the seemingly barren nature of the Degenerate-era universe, it's possible that some forms of complexity or even life might still exist during this epoch. Hypothetical civilizations that survive into this era would need to adapt to an environment where energy sources are extremely scarce and matter itself is slowly disappearing. Such beings might need to harness the energy released by proton decay or find ways to manipulate quantum processes to maintain their existence. The possibility of life during the Degenerate era raises profound questions about the nature of consciousness and intelligence. Could information processing systems be constructed from the elementary particles and radiation that populate this epoch? Might forms of life exist that are so different from biological organisms that we can barely recognize them as alive? These questions touch on the deepest mysteries of consciousness and the relationship between mind and matter. As we contemplate the vast stretches of time that define the Degenerate era, we are reminded of the temporary nature of all the structures and phenomena we observe in the present universe. Stars, planets, galaxies, and even atoms themselves are ultimately transient features in the cosmic story. Yet, even as matter dissolves through proton decay, the fundamental laws of physics continue to operate, ensuring that the universe remains a stage for whatever phenomena the far future might bring. The Degenerate era represents not an ending, but a transformation, a cosmic metamorphosis that will reshape the very foundations of reality itself. Black hole era and Hawking radiation. After the last proton has decayed and the Degenerate era draws to its close, the universe enters perhaps its most mysterious and fascinating epoch. This is the black hole era, a time when these enigmatic objects will dominate the cosmos, standing as the last bastions of organized matter in an otherwise empty and cold universe. Yet, even these seemingly eternal monuments to gravitational collapse are not immune to the inexorable march of time and the strange predictions of quantum mechanics. Black holes have captivated human imagination since their theoretical prediction over 2 centuries ago. Originally conceived as dark stars by John Michell in 1783, these objects represent regions of spacetime where gravity has become so intense that nothing, not even light, can escape once it crosses a certain boundary known as the event horizon. For most of their scientific history, black holes were considered perfect absorbers, cosmic vacuum cleaners that could only grow larger as they consume matter from their surroundings. This perception changed dramatically in 1974 when Stephen Hawking made one of the most surprising discoveries in theoretical physics. Using the principles of quantum mechanics near the event horizon of a black hole, Hawking showed that these objects are not perfectly black after all. Instead, they emit a faint radiation that slowly but steadily causes them to lose mass and energy. This Hawking radiation represents a fundamental connection between gravity, quantum mechanics, and thermodynamics that continues to challenge our understanding of the universe. To understand Hawking radiation, we must delve into the quantum nature of empty space itself. According to quantum field theory, what we perceive as vacuum is actually a seething foam of virtual particle pairs that constantly pop into existence and annihilate each other. These quantum fluctuations occur everywhere in space, but near the event horizon of a black hole, something remarkable happens. Occasionally, one particle from a virtual pair falls into the black hole, while its partner escapes into space. The escaping particle becomes real, appearing as Hawking radiation, while the particle that fell in carries negative energy, effectively reducing the black hole's mass. The temperature of Hawking radiation is inversely proportional to the black hole's mass. This creates a fascinating paradox. As a black hole loses mass through Hawking radiation, it becomes hotter and radiates away its remaining mass even faster. Massive black holes have extremely low temperatures, emitting radiation so faintly that they are essentially invisible against the cosmic microwave background. But as they shrink, they gradually heat up, entering a runaway process that culminates in explosive evaporation. During the black hole era, the universe will be populated primarily by black holes of various masses, each following its own timeline toward ultimate evaporation. Stellar mass black holes, formed from the collapse of massive stars, will have initial masses ranging from about 3 to several dozen solar masses. These objects will persist for enormous periods, with evaporation times proportional to the cube of their mass. A black hole with the mass of our Sun would take approximately 10 to the 67th power years to completely evaporate, a span of time so vast that it makes the proton decay timescale seem brief by comparison. Supermassive black holes, the giants that currently lurk at the centers of galaxies, will dominate the early phases of the black hole era. These monsters, with masses ranging from millions to billions of solar masses, will persist for truly astronomical periods. The largest supermassive black holes might take more than 10 to the 100th power years to evaporate completely, meaning they will outlast even the longest-lived stellar remnants by factors that defy comprehension. The process of black hole evaporation is not uniform or steady. For most of their lifetime, black holes lose mass extremely slowly, radiating at temperatures far below the cosmic microwave background. During this phase, they are effectively invisible, detectable only through their gravitational effects on nearby matter. However, as they approach the final stages of evaporation, their temperature rises dramatically, and they begin to emit increasingly energetic radiation. The spectrum of Hawking radiation is thermal, resembling the glow of a perfect black body radiator. For large black holes, this radiation consists primarily of photons with wavelengths longer than the size of galaxies. As the black hole shrinks, the characteristic wavelength of the radiation decreases, progressing through radio waves, microwaves, infrared light, visible light, ultraviolet radiation, X-rays, and eventually gamma rays. In the final moments of evaporation, a black hole becomes incredibly hot, potentially reaching temperatures of billions of degrees. The composition of Hawking radiation also evolves as a black hole evaporates. Initially, the radiation consists almost entirely of massless particles, photons and possibly gravitons. As the black hole's temperature increases, it begins to emit massive particles as well, including electrons, muons, and eventually even protons and other hadrons. In the final microseconds of evaporation, the black hole might emit all types of elementary particles, creating a spectacular fireworks display of matter and antimatter. During the black hole era, the universe will be an incredibly sparse and cold place. The expansion of space will have stretched the cosmic microwave background radiation to wavelengths measured in light years, reducing its temperature to a tiny fraction of a degree above absolute zero. In this frigid environment, the faint glow of Hawking radiation from evaporating black holes will provide the only sources of energy and light in the cosmos. The gravitational effects of black holes will continue to shape the structure of space during this epoch. Black holes will orbit each other in binary systems, gradually spiraling inward as they lose energy through gravitational wave radiation. When two black holes finally merge, they create ripples in space-time that propagate across the universe at the speed of light. These gravitational waves represent one of the few dynamic processes that will occur during the otherwise quiet black hole era. The merger of black holes also provides a mechanism for creating new black holes with different masses and properties. When two stellar mass black holes combine, they form a single black hole with a mass slightly less than the sum of the original masses, with the difference converted into gravitational wave energy. These merger events will occasionally occur throughout the black hole era, temporarily disrupting the slow, steady process of evaporation with bursts of gravitational radiation. Primordial black holes, if they exist, will play a special role during the black hole era. These hypothetical objects would have formed in the early universe from density fluctuations shortly after the Big Bang. Unlike stellar mass black holes, primordial black holes could have a wide range of masses, from microscopic to stellar scales. The smallest primordial black holes would evaporate quickly, potentially contributing significant amounts of energy to the early universe. Larger primordial black holes might persist well into the black hole era, providing additional sources of Hawking radiation. The information paradox, one of the most profound puzzles in modern physics, becomes particularly relevant during the black hole era. When matter falls into a black hole, it appears to carry information about its quantum state with it. However, Hawking radiation appears to be purely thermal, containing no information about the matter that created it. This suggests that information might be destroyed when black holes evaporate, violating one of the fundamental principles of quantum mechanics. Various solutions to this paradox have been proposed, including the possibility that information is somehow encoded in the subtle correlations of Hawking radiation. The holographic principle, which suggests that all the information in a volume of space can be encoded on its boundary, offers one potential resolution to the information paradox. According to this principle, the information that falls into a black hole might be preserved on the event horizon itself, encoded in the microscopic structure of space-time. When the black hole evaporates, this information could be released in the Hawking radiation, though in such a scrambled form that it would be practically impossible to decode. String theory and other approaches to quantum gravity have suggested additional complexities to black hole evaporation. Some models predict that black holes might not evaporate completely, instead leaving behind tiny remnants with masses near the Planck scale. These remnants could persist indefinitely, potentially serving as repositories for the information that originally fell into the black hole. Other theories suggest that black holes might undergo phase transitions during evaporation, temporarily halting the process before resuming with different characteristics. The concept of black hole thermodynamics becomes crucial during the black hole era. Black holes obey laws analogous to the laws of thermodynamics, with their event horizon area playing the role of entropy and their surface gravity corresponding to temperature. The second law of thermodynamics, which states that entropy always increases, translates into the principle that the total area of all black hole event horizons in the universe can never decrease. This law governs the merger and evaporation processes that define the black hole era. During the later stages of the black hole era, as smaller black holes begin to evaporate noticeably, the universe will experience brief periods of illumination. A black hole in its final stages of evaporation will shine with the brightness of a star, though for only a relatively short time. These evaporation events will be scattered randomly throughout space and time, creating isolated beacons of light in an otherwise dark cosmos. The final moments of black hole evaporation are predicted to be particularly dramatic. As a black hole shrinks to microscopic size, its temperature soars to incredible heights, and it radiates away its remaining mass in a final explosion. This terminal burst might release as much energy as a modest nuclear weapon, though the energy would be distributed across all types of particles and radiation. The explosion would be over in a fraction of a second, leaving behind only elementary particles and electromagnetic radiation. The end of the black hole era marks a transition point in cosmic evolution. Once the last black hole has evaporated, the universe will enter a new phase where gravity plays a much diminished role. Without the organizing influence of massive objects, matter and energy will be distributed almost uniformly throughout space, with only tiny quantum fluctuations providing any variation in density or temperature. The timescales involved in the black hole era are so vast that they challenge our ability to comprehend them meaningfully. A stellar mass black hole will persist for longer than a Google years, a number so large that it exceeds the number of atoms in the observable universe. Supermassive black holes will endure for periods that require scientific notation just to express, existing for so long that entire cycles of cosmic evolution could occur multiple times during their lifetime. Yet even these astronomical timescales pale in comparison to the age the universe will achieve by the end of the black hole era. When the last supermassive black hole finally evaporates, the universe will be older than 10 to the 100th power years, an age so advanced that our current 13.8 billion-year-old cosmos appears as merely the first instant of cosmic dawn. The black hole era also raises profound questions about the nature of time itself. In a universe dominated by slowly evaporating black holes, change occurs so gradually that the concept of temporal flow becomes almost meaningless. Billions of years might pass without any significant alteration in the cosmic environment. Only the patient process of Hawking radiation provides a universal clock, marking the inexorable passage of time through the gradual disappearance of mass and energy. Some theoretical models suggest that the universe might undergo cycles of expansion and contraction, with each cycle beginning with a big bang and ending with a big crunch. In such cyclic cosmologies, the black hole era might represent the final phase before gravitational collapse reverses the expansion and triggers a new cosmic cycle. However, current observations suggest that the expansion of the universe is accelerating due to dark energy, making such cyclic scenarios less likely. The possibility of life existing during the black hole era presents fascinating challenges to our understanding of biology and intelligence. Any organisms that survive into this epoch would need to adapt to an environment where energy sources are incredibly scarce and widely separated in space. They might need to hibernate for millions of years between brief periods of activity or develop technologies that can harness the faint energy of Hawking radiation. Advanced civilizations might even attempt to manipulate black holes during this era, using them as sources of energy or as tools for information processing. The immense gravitational fields near black holes could be exploited for time dilation effects, allowing inhabitants to experience accelerated time, while the rest of the universe ages around them. Such civilizations might become the universe's final witnesses, observing the slow death of the cosmos from their vantage points near event horizons. As we contemplate the black hole era and the strange phenomenon of Hawking radiation, we are reminded of the deep connections between seemingly unrelated areas of physics. The evaporation of black holes links quantum mechanics, general relativity, and thermodynamics in ways that continue to surprise and challenge physicists. These connections suggest that our universe operates according to principles that are more subtle and interconnected than we might initially suppose, with each fundamental force and particle playing a role in the cosmic drama that unfolds over time scales beyond human imagination. Gravitational entropy collapse. In the cosmic timeline, after the last black hole has evaporated through Hawking radiation, and the universe has entered an era of seemingly complete dispersal, there emerges a phenomenon so subtle yet profound that it challenges our understanding of the very nature of space, time, and gravity itself. This is gravitational entropy collapse, a process that operates on time scales so vast that even the black hole era appears brief by comparison, yet which may represent the universe's final attempt to organize itself against the relentless march toward maximum entropy. To comprehend gravitational entropy collapse, we must first understand the peculiar nature of gravity among the fundamental forces. Unlike electromagnetism or the nuclear forces, gravity has the unique property that it becomes stronger as matter clusters together. When gravitational systems collapse, they actually decrease in entropy locally, while increasing the total entropy of the universe through the radiation they emit. This counterintuitive behavior makes gravity fundamentally different from other forces, and gives it a special role in the far future evolution of the cosmos. Entropy, the measure of disorder in a system, generally increases over time according to the second law of thermodynamics. In most physical processes, energy disperses, temperatures equalize, and systems evolve toward states of maximum randomness. However, gravity introduces a fascinating complication to this picture. Gravitational systems can spontaneously organize themselves into more ordered configurations, creating structure and complexity even as the overall entropy of the universe continues to increase. During the era following black hole evaporation, the universe will consist primarily of elementary particles scattered throughout an enormously expanded space. Electrons, positrons, neutrinos, and photons will drift through a cosmos that has grown so large and cold that these particles are separated by distances measured in light years. The temperature of space will have dropped to levels so close to absolute zero that thermal motion becomes negligible, and quantum effects begin to dominate the behavior of matter and energy. In this seemingly sterile environment, gravity continues to operate according to Newton's inverse square law and Einstein's general relativity. Even the most tenuous concentrations of matter create gravitational fields that extend throughout space, weakening with distance but never completely disappearing. Over the immense timescales of the post-black hole era, these incredibly weak gravitational influences can accumulate and produce measurable effects. The process of gravitational entropy collapse begins with tiny density fluctuations in the distribution of particles throughout space. These fluctuations might arise from quantum mechanical effects, from the remnants of ancient cosmic structures, or from the random clustering that inevitably occurs in any finite collection of particles over sufficient time. Once a region of space contains even a slightly higher density of matter than its surroundings, gravity begins to enhance this overdensity. As particles are drawn toward these overdense regions, they gain kinetic energy from the gravitational potential wells they are falling into. This process converts gravitational potential energy into kinetic energy, heating the infalling matter and causing it to radiate electromagnetic energy into space. The radiation carries away energy and entropy, allowing the gravitational system to become more tightly bound and organized than it was initially. The timescales involved in gravitational entropy collapse are almost incomprehensibly long. The gravitational attraction between particles separated by light years is extraordinarily weak, and the process of drawing them together operates at a pace that makes stellar evolution appear rapid by comparison. Individual particles might drift toward gravitational attractors for periods measured in Google years or longer, slowly gaining speed as they fall through ever-deepening potential wells. However, the mathematics of gravitational collapse reveals that once this process begins, it tends to accelerate. As matter becomes more concentrated, the gravitational fields strengthen, attracting additional particles from ever greater distances. What begins as an almost imperceptibly slow drift gradually evolves into a more rapid infall, though rapid in this context still means timescales far exceeding anything we can directly comprehend. The ultimate fate of these gravitational collapse events depends on the total amount of matter involved and the precise dynamics of the infall process. In some cases, the collapsing matter might form structures reminiscent of the stellar remnants from earlier cosmic epochs. Regions with sufficient density might undergo a kind of reverse evaporation, concentrating diffuse particles back into compact objects that could potentially evolve into new types of stellar or planetary bodies. More dramatically, if enough matter participates in a gravitational collapse event, the system might undergo runaway collapse similar to the formation of black holes in earlier cosmic epochs. Once the escape velocity from a collapsing region exceeds the speed of light, a new black hole forms, recreating the very objects that dominated previous eras of cosmic evolution. These new black holes would then begin their own slow evaporation through Hawking radiation, potentially initiating new cycles of cosmic evolution. The possibility of black hole formation through gravitational entropy collapse raises profound questions about the ultimate fate of the universe. If collapsed regions can spontaneously form new black holes, and if these black holes can subsequently evaporate and disperse their matter back into space, the cosmos might undergo endless cycles of collapse and dispersal. Each cycle would operate on time scales vastly longer than the previous ones, creating a kind of cosmic breathing that could continue indefinitely. Quantum mechanics introduces additional complexity to the gravitational entropy collapse scenario. At the incredibly low temperatures characteristic of the post-black hole era, quantum effects become dominant in determining particle behavior. Quantum tunneling might allow particles to overcome energy barriers that would be insurmountable in classical physics, potentially accelerating the collapse process or allowing it to proceed along pathways that classical mechanics would forbid. The uncertainty principle also plays a role in gravitational entropy collapse. As particles become localized in space through gravitational attraction, their momentum becomes increasingly uncertain, leading to quantum mechanical spreading that opposes further concentration. This creates a fundamental tension between gravitational attraction and quantum mechanical repulsion that might ultimately limit how compact the collapsed structures can become. Zero-point energy, the irreducible quantum mechanical energy that exists even at absolute zero temperature, could also influence gravitational entropy collapse. As matter becomes more concentrated, the zero-point energy of the confined particles increases, potentially providing a source of pressure that resists further collapse. This quantum mechanical effect might prevent the formation of singularities or other pathological objects during the collapse process. The role of dark matter in gravitational entropy collapse remains highly speculative but potentially crucial. If dark matter particles are stable over the timescales of the post-black hole era, they could provide the dominant gravitational influence driving collapse events. Dark matter's lack of electromagnetic interactions would prevent it from radiating away energy during collapse, potentially allowing for the formation of more massive and long-lived collapsed structures than would be possible with ordinary matter alone. Alternatively, if dark matter particles decay over extremely long timescales, they might provide a continuing source of ordinary matter and energy throughout the post-black hole era. The decay of dark matter could inject new particles into the cosmic environment, potentially triggering additional gravitational collapse events or providing the raw material for new forms of cosmic evolution. The concept of vacuum decay introduces another layer of complexity to gravitational entropy collapse scenarios. Some theories suggest that the quantum vacuum might not be in its lowest possible energy state, but rather in a metastable state that could eventually decay to a lower energy configuration. If vacuum decay occurs during the era of gravitational entropy collapse, it could dramatically alter the physics governing the collapse process, potentially accelerating it or changing its ultimate outcome. Vacuum decay events might propagate through space as expanding bubbles of true vacuum, converting false vacuum regions to lower energy states. These bubbles would expand at the speed of light, potentially triggering or disrupting gravitational collapse events as they pass. The interaction between vacuum decay and gravitational collapse could lead to complex patterns of cosmic evolution that are difficult to predict with current theoretical tools. The possibility of gravitational entropy collapse also raises questions about the nature of time and causality in the far future universe. During the extremely slow initial phases of collapse, the concept of simultaneity becomes problematic due to the vast distances involved and the finite speed of light. Events that are causally connected through gravitational interactions might be separated by millions or billions of years, creating a universe where cause and effect operate on time scales that dwarf human comprehension. Einstein's general relativity predicts that strong gravitational fields can significantly affect the flow of time through time dilation effects. As matter collapses into increasingly dense configurations, observers near the collapsing regions would experience time passing more slowly relative to observers in the nearly empty space between collapse sites. This could create a universe where different regions evolve at dramatically different rates, with some areas experiencing rapid change while others remain essentially frozen in time. The possibility of closed time-like curves, theoretical pathways through space-time that could allow travel into the past, might also emerge during extreme gravitational collapse events. While such exotic space-time geometries are generally thought to be unstable or forbidden by quantum effects, the extreme conditions during gravitational entropy collapse might create environments where our current understanding of causality breaks down. Information theory provides another perspective on gravitational entropy collapse. The process of gravitational collapse concentrates matter and energy, potentially increasing the information density in localized regions of space. This concentration of information might allow for the emergence of complex structures or even primitive forms of computation, creating islands of information processing in an otherwise informationally sparse universe. The holographic principle, which suggests that all information in a volume of space can be encoded on its boundary, might become particularly relevant during gravitational collapse events. As matter falls into increasingly compact configurations, the information describing its quantum state might be preserved on the surfaces of the collapsed objects, potentially allowing for the recovery of information even after the collapse process is complete. Entropy collapse events might also create environments suitable for the formation of complex molecules or even primitive life forms. As matter concentrates and heats up during gravitational infall, it might reach temperatures and densities where chemical reactions become possible once again. These brief episodes of chemical activity could potentially lead to the synthesis of organic compounds or other complex structures that would be impossible in the cold, dispersed environment of the post-black hole era. The energy released during gravitational collapse could also power other interesting physical processes. High-energy particle collisions might occur as matter streams toward collapse sites, potentially creating exotic particles or triggering nuclear reactions. These processes could inject new forms of matter and energy into the cosmic environment, providing the raw materials for subsequent evolution. Advanced civilizations, if any survive into the era of gravitational entropy collapse, might attempt to harness or control these processes for their own purposes. They might seed the universe with carefully placed mass concentrations designed to trigger controlled collapse events, using the energy released to power their activities over the vast timescales of the far future. Such civilizations might become cosmic gardeners, cultivating gravitational collapse events as sources of energy and complexity in an otherwise sterile universe. The study of gravitational entropy collapse also illuminates fundamental questions about the nature of cosmic evolution and the ultimate fate of organized matter. Does the universe inevitably evolve toward a state of maximum entropy and minimum structure? Or do gravitational effects provide a mechanism for the spontaneous generation of complexity even in the far future? The answer to this question has profound implications for our understanding of cosmic purpose and the possibility of eternal cosmic evolution. Current cosmological observations suggest that the expansion of the universe is accelerating due to dark energy, which could potentially prevent or significantly delay gravitational entropy collapse events. If dark energy continues to drive accelerated expansion, it might overcome gravitational attraction on all but the smallest scales, preventing the formation of new collapse structures and ensuring that the universe evolves toward a state of maximum dispersal and minimum organization. However, our understanding of dark energy remains limited, and it's possible that its properties might change over the vast timescales of the far future. If dark energy weakens or changes sign, it could allow gravitational entropy collapse to proceed as described, potentially leading to new cycles of cosmic evolution that we cannot currently predict or understand. As we contemplate the possibility of gravitational entropy collapse in the far future universe, we are reminded of the deep connections between gravity, thermodynamics, and information theory that govern cosmic evolution. Even in a universe that appears to be winding down toward heat death, the unique properties of gravitational attraction might provide pathways for the emergence of new forms of order and complexity. Whether these processes represent the universe's final creative acts or the beginning of new cycles of cosmic evolution remains one of the most profound questions in cosmology, touching on the deepest mysteries of existence itself. I hope you enjoyed this journey through the possible endings of our universe. If you did, I'd appreciate a thumbs up and a subscription. If you're still awake, there's another video waiting for you right here on the screen.